side event on metrology. So I will just give a small introduction as we allow a little bit more time for more participants to join. So first, I want to welcome you. My name is Benoît Doury. I'm with CTBTO, and I'm very pleased to open this event on behalf of CTBTO. So the overall goal of this session is to explore metrology for seismic, hydroacoustic, and infrasound technologies. Why is it important? Because metrology ensures traceability, data reliability, and long-term sustainability of the IMS network. And we hope that this event will provide a forum to connect scientists, metrologists, manufacturers, and operators to share progress and challenges in metrology. Among the objectives of this session, we would like to review the most recent state-of-the-art developments in metrology, which is relevant to the IMS SHA technologies. We hope to discuss how laboratory calibration capabilities can be translated into field calibration methods, and to highlight technical challenges and research needs for full implementation in the IMS context. We would also like to encourage a wider adoption of unified calibration approaches, which would be compatible with IMS requirements. So how the event will be structured, it's lasting 3.5 hours. The first 3 hours will be dedicated to oral presentations, each lasting 20 minutes, which includes Q&A. 2 of the presentations will be given remotely, so in case we have some problems with the connection, we have a backup, so don't be surprised in case we need to adapt at that point. So we have, like I said earlier, 3 thematic areas: seismic, hydroacoustic, and infrasound, and each will be chaired by an expert. And at the end of the event, we have reserved 30 minutes for comments, suggestions, and a broader discussion with the chairs and the presenters. Now I would like to introduce the chairs. On the right, we have Mr. Stephen Robinson from NPL, UK. Dr. Robinson has 27 years experience in underwater acoustic metrology. He's a chair of ISO TC43 and IEC TC87, and he's a principal research scientist at NPL, leading in underwater acoustic standards. Then we have Dr. Peggy Helweg, from former UC Berkeley, US. She spent her career dedicated to understanding and evaluating seismic instrumentation performance. And she has recently taken the leadership in bringing seismology and metrology communities together. For instance, at the ESC in Greece, the European Seismological Commission event that happened last year in September, and at the SSA in the US this spring. Now I would like to transition to the first presentation, which will be given by my colleague, Atajan Koraki, and he will be providing an overview of the CTBTO's metrology objectives and ongoing efforts toward quality assurance. Oh, sorry, I skipped. Yeah. Yes, and the third panelist is Dr. Richard Baham from ASN UK. He's a specialist in acoustic calibration for infrasound and underwater acoustics. And Dr. Baham's key role in infra AUV project was very important, and he has been supporting CTBTO for some time already to advance CTBTO in its metrology roadmaps. Richard also brings broad expertise linking the infrasound and hydroacoustic metrology to the SI.
Okay. So actually Benoît and Richard working very closely to each other, so that's why maybe Benoît just had forgotten. Oh, okay. Good morning to everyone. So it's nice to see you again in here. So as my colleague Benoît mentioned, I will briefly introduce the overview of requirements, challenges, and the current status of the IMS network from a metrology perspective. But later on each technology specific topics will be presented. So just we'll give a brief introduction in here. So first of all, I also would like to thank you for participating in this site event at SNT 2025. We would like to thank you for your participation, and I hope that it will be a fruitful session for everyone. I also would like to thank chairpersons and my colleague for their contribution and making this event possible. So my name is Ch2. I'm the head of hydroacoustic unit in the engineering and development section of the IMS division at CTBTO. So today I will give an overview of requirements, current status, and the future plans of IMS stations from meteorology perspective. So we all know the treaty and its verification regime. So the IMS International Monitoring System is one of the key components of the verification regime, and the IMS is based on 4 technology, 3 waveform technologies and and radionuclide technologies, particle technologies. So seismic, hydroacoustic, and the infrasound are the 3 waveform technologies, and radionuclide is the technology that detects the noble gases and radioactive particles, but today we will just discuss about the first 3 waveform technologies. So in this slide you also see how many stations are already certified and installed. So that was mentioned also yesterday, so 90%, about 90% of the stations are already built, and they are sending data to IDC in Vienna. So the quality assurance. I would like to briefly mention the component of the verification regime of the treaty. So there are 4 components. IMS is one of that. And it's together with the IDC, so the measured signals are transmitted to the International Data Center for data processing. And the other components, which I am not going to go into detail, are consultation and clarification, on-site inspection, and confidence building measures. So these are the verification regimes that make the treaty on the center. So quality assurance, so IMS quality assurance process is derived from the operational manuals, from the requirements in the operational manuals. So we have 4 stage of quality assurance process. So the first one is the type approval. So you see on the left side of the screen. So the new model of the subcomponents of monitoring technologies is tested extensively to verify that they meet IMS requirements before being accepted for use in the IMS network. Second stage is the device acceptance. So acceptance tests are performed on individual devices, so on each device with the serial number before they are deployed to the station. Third one is the initial calibration. So the new system is tested under operational conditions to determine its nominal response. And the last one is on-site calibration. So the full frequency response of the operational system is measured and then compared with the initial calibration result.
Pronto, mi sente? Buongiorno. Pronto, mi sente?
Sorry.
Pronto, mi sente?
So the on-site calibration is performed periodically. When there is a replacement of an equipment, the process returns to the device acceptance stage, and then the initial calibration and on-site calibration are done again. So from now on, I will speak about the current meteorology status and the future plans of each technology. So at the top side of my slide, you see the IMS monitoring range in terms of frequency, and the current CMCs. At the bottom, you see the current level of implementation shown with a color bar from laboratory to field. So the same representation will be used for each technology, but at the end of this session, during the discussion session, we will go into deep and discuss more about the solution, what should be the solutions to implement these meteorological activities to the IMS station. So for the IMS seismic stations, the frequency range of the interest for seismic stations is from 20 millihertz to 5 hertz, and there are no validated CMCs at frequencies below 0.1 hertz. So on the laboratory calibration side, with the recent event that was completed in 2023, Euromet Infra-AUE project, laboratories and NMIs have adapted their workbenches to calibrate large seismometers, because normally they calibrate accelerometers in their workbench, but this adaptation was done during this project. Some concepts are being studied for primary and secondary laboratory calibrations. PTS, together with the expert laboratories, has developed draft quality assurance documents for the type approval and device acceptance of seismometers and digitizers. And for initial and on-site calibration, PTS relies on electrical self-calibration for seismic and hydroacoustic T-phase stations, which presents some operational complexity and limitation. For a hydroacoustic hydrophone station, the frequency range of interest for IMS hydrophone station is from 1 hertz to 100 hertz, and there are no validated CMCs at the frequencies below 250 hertz. The primary standard calibration setups are still not well established worldwide. There are a few NMIs that have this capability in the frequency range from 1 hertz to 100 hertz. And on the laboratory side, with the recent Euromet project, laboratories have expanded their secondary calibration setups down to 1 hertz, and interlaboratory comparison measurements have been done successfully, and positive results were obtained. The implementation of ocean conditions is another challenge. Efforts are ongoing to introduce environmental effects into calibration infrastructures. And for the on-site calibration, as you know from the yesterday presentation, at the present only the electronics of the underwater segment can be calibrated after deployment. However, in-situ full chain calibration in the low frequency range is still missing. And the last technology about the current status, so infrasound, the frequency range is same as seismic, and there are no validated CMCs yet, but the calibration capabilities are more mature compared to other two technologies. There are several concepts and methods have been developed by NMIs and IMS service providers, and comparison measurements demonstrate promising results between expert laboratories for the majority of the IMS frequency range. And the first accreditation of a laboratory has been achieved for the IMS frequency band of interest. And for the initial and on-site calibration, the good progress has been made with the rollout of passive calibration capabilities with Gabrielson method at IMS station, and the software CalixPy supports calibration of infrasound measurement system both in the laboratory and on-site. So I have 3 more slides about the future calibration plans for each technology. So first, seismic. So future calibration capability plan for IMS seismic stations. So PTS is developing a roadmap to develop seismic metrology. The metrology community continuously research to advance laboratory calibration methods that link seismic measurement to the SI units. So pilot studies and comparison are being formulated to validate the measurement capabilities of the NMIs and expert laboratories. And we maintain the continuous communication with the stakeholder. For initial and on-site calibration, PTS is further developing the SSI software for electrical calibration at IMS seismic stations. And for the existing and alternative on-site calibration practices are under review, and PTS encourage the community to conduct additional research on site-by-site calibration. About the hydroacoustics, so as it's the technology that I am representing, so I can give some more maybe insight. So we assume that the primary sensing element is the hydrophone, and that can degrade over time due to the aging, electronic aging, water ingress, or the external impact. So since IMS hydrophone stations must operate beyond their design life, so early detection of aging is essential. So therefore, full chain in situ calibration can help us to identify issues, support maintenance, and ensure long-term reliability. The goal is to extend low-frequency calibration capabilities in the frequency range from 1 Hz to 100 Hz across the NMIs and DIs, while also incorporating ocean conditions such as depth and temperature into standards. And the infrasound, so the expansion of the comparison cycle to ensure equivalence between NMIs and expert laboratories, and conduct pilot studies to develop and validate their measurement capabilities, so as a future activity. Maintain continuous communication with the stakeholders, and encouraging ongoing efforts to establish CMCs and advance research on environmental susceptibility. For the initial and on-site calibration, the rollout of calibration capabilities at infrasound stations will continue. The process for using traveling standards will be formalized and implemented to regularly establish traceability to the SI units. And a pilot study will be conducted using QC metrics based on historical IMS infrasound calibration data to evaluate potential benefits. So as a conclusion, so calibration capabilities are expanding but remain limited for IMS frequency band, with formal CMCs still pending. So further understanding of instrument behavior over time is needed, particularly regarding environmental susceptibility, and also on-site calibration remains challenging for seismic and hydroacoustic systems, while infrasound methods are advanced and being implemented. So overall, quality assurance, investment, and roadmaps are aligned with long-term IMS sustainment goals. So with that, I would like to thank you for listening. And just as information, further communication can be done through myself and with my colleague related on the relevant subject. So again, thank you for your listening. And
Thank you very much, Jan. We've got several more technical presentations to come, a lot of which will substantiate some of the elements that Jan has talked about in his presentation. But we've got time for a quick question. If somebody has some question on the current status and current thinking within PTS. Does anyone have a question? Thomas.
My name is Thomas Bruns. I'm from the National Metrology Institute of Germany, PTB, and I just want to add something because the abbreviation CMC was mentioned several times, and not everyone may be aware what it means.
Yeah,
CMCs are basically the internationally accepted lowest measurement uncertainties that the National Metrology Institutes can apply without being tested for it directly. They are validated by key comparisons between the institutes and therefore reliable. But this is something that's actually registered and internationally approved. Thank you.
Thank you, Thomas. Useful to point
thank you
out.
for the comment, Thomas.
Yeah, for the next talk, we'll have, is there one more question? There's one, we have time for the one more question.
Yeah, I do have a quick question. Could you elaborate on environmental susceptibilities? It's not clear to me whether you're talking more about, operation in a wet or salty environment, or whether you're talking about susceptibility to magnetic fields for a seismometer, for example, or air pressure or temperature.
For each technology, it depends. But for hydroacoustic, like the depth and the temperature is that can be the effects for the susceptibility. So it's all the effects that comes from the environment actually that can degrade the frequency response of the transducer or the sensor.
I can probably add a little to that. My understanding is there are two categories of environmental impacts. One is the ongoing impact on performance in situ, for example, the temperature and pressure and so on. And then there's the resilience to things like transportation and salt sprays and all the other environmental impacts that can come. So both are important.
Thank you very much, John.
You're welcome.
Our next speaker will be Horst Rademacher. And I have to wake up my screen. The title of his presentation is The Challenges Precisely Measuring Ground Motion Uncertainties and Calibrations.
Yeah, good morning, everybody. Thank you for attending the side event. I retired from UC Berkeley, and I was responsible for checking seismometers before we deployed them in the field. So I have also quite a bit of experience in dealing with uncertainties and the precision of instrumentation. I would like to point out that in contrast to the other two technologies that we apply in the IMS, seismology is much older. It was developed way before the first nuclear explosion ever happened. So we are looking back at a long, long history of how to calibrate instrumentation of various generations of instrumentation. So does this move? No, it doesn't move. No? Sorry.
I think you have to say next slide.
Maybe I say next slide. Does that work? Yes, that works. So you can all read the disclaimer. I'm trying to be as neutral as possible regarding the instrumentation. I know there are there are manufacturers maybe here in this room, so please don't hold me to their advertisements. Anyway, so does it? No, it doesn't move. No? Sorry.
I think you have to say next slide.
Maybe I say next slide. Does that work? Yes, that works. So you can all read the disclaimer. I'm trying to be as neutral as possible regarding the instrumentation. I know there are there are manufacturers maybe here in this room, so please don't hold me to their advertisements. Anyway, so does it work now? Yes. So the challenges for measuring ground motion. The motivation of this whole session is to talk about instrumentation and the calibration of instrumentation for the three technologies, as we heard in the two previous talks, and the traceability to SI standard. But my motivation for giving this contribution is to help you understand the complexities and difficulties in operating seismic stations. And there are lots of networks besides the IMS that operate seismic stations and networks successfully for decades. And I want to show that the calibration of a seismic instrument, of a seismometer itself, is an absolute necessary element in looking at seismic stations, but it's not enough. It's not sufficient. We need to do much more in order to understand the performance of a seismic station. So what do we want to measure with the seismometer or with the seismic station? We want to measure the ground motion with the highest possible precision, with the least uncertainties, the lowest noise possible, which is a very important factor in the detectability of any event. It doesn't matter if it's a tectonic event or if it's a underground nuclear explosion. And we want to measure it, and that's also very important, in real units. We really want to know, has the ground moved, how many centimeters or micrometers per second or millimeters per second square has the ground moved? And that's independent of CTBTO or other uses, because an engineer who wants to build a good earthquake-resistant building needs to know what these measurements are. So these are great goals, but they are, it's not so easy to achieve them. We need a very complex measurement system. It's not just a seismometer. And such a system is commonly called a seismic station. And it consists of many elements, and I've listed a few here: seismometer, digitizer, clock, data management and storage, and the telemetry. And these are the instrumental elements. But then there are also environmental elements that we have to deal with in order to make the performance acceptable. And these are, for instance, thermal and other insulations that we have to construct around the seismometer and other elements of the seismic station. And we have to look at the geologic conditions. You know, is there tilt? I mean, there are many stations, not for the CTBTO, but in other networks, they are on volcanoes and there's tilt. What effect do these changes in geologic conditions have on the measurement? So we have to understand them all and how they are working together in order to get reliable seismic measurements. So what does that mean for ground motion? Each of the elements that I'm talking about has its own precision. So the seismometer precision in the various pass bands is different than, for instance, the precision of the digitizer. And we have to understand them. And they have specific uncertainties, each of these elements. That also means that each of the elements, a seismometer or a digitizer or a clock, need its own calibration. We can't have a good seismic station with a clock that is not calibrated and we don't know how precise it actually is. When was the onset that we measure? So just the calibration of a seismometer gives us, I think, limited information about the overall health of the station. So that is a very important part, the state of health. So the calibration of a seismometer is necessary, but it's definitely not sufficient. So how does the calibration of a seismometer work? And I'm going now back to times before we even had nuclear explosions. For instance, the Wiechert instrument, which was one of the oldest instruments 120 years ago or so, you just took a penny or a cent and put it on the mass and see how the system reacted to the difference between the original mass and an additional mass that you put on the inertial mass. Or another element is, I mean, I was never very good at it because my musical hearing is about non-existent, but you could measure the performance of a Benioff instrument, which is on the right, with a tuning fork. And there were some seismologists who were very good at it. I was never good at it. But anyway, so there are various means that had been developed in the time of mechanical seismographs to calibrate. And what was the result of that calibration? It was not something that we want to have today, measurement of the ground motion really in real units, but all we could do is measure the magnification of the ground motion. How much did this particular seismograph system enhance and amplify the ground motion? Now, in the modern era, of course, all seismometers are very different. You don't see these old instruments anymore. You have three components, usually in one housing. You can have different internal layouts of how the components are arranged. There are at least two. You can have more, but there are at least two that are realized in commercial instruments. One is the classic orthogonal layout, and the other one is a tilted layout after Galperin's paper in 1955. And then, more important even, is the feedback. And there are different designs of the feedback loop that govern the response of the seismometer. And there are currently two methods of how to calibrate a seismometer. One is the mechanical, and we have many experts here who have used mechanical shake tables, precision shake tables to measure the response. Or the second one is an electrical method by injecting a well-known signal of a certain voltage or of a certain amperage into the feedback system in order to see how the mass is responding to it. And there are various, so both of them are, the methods are both valid, but they yield different insights. For instance, the mechanical gives a little bit more information about the internal component layout. So if you have a classic or orthogonal system, you can really get information about how each component operates separately from the others. And we get some information about the behavior of the internal mass and of the feedback system. And Thomas Bruns, later here in this session, will talk about both of these types of lab calibration. But as I said several times now, this is important. This is necessary, but this is not sufficient. We need to have more information about the seismic system. And here are the other elements that I mentioned before. The digitizer. It's actually one of the most important elements of a seismic system, because with the voltage alone, the output voltage of a seismometer, we can't do anything. It's great, yes. Oh yeah, we can measure it with a voltmeter, but that's not what we want. We want to understand how this voltage is related to ground motion. And you can only do this in the modern world with an appropriate digitizer. And that needs to have a separate calibration. It's a totally different way of calibrating because it's a digital device. The clock needs to be calibrated separately. I mean, mostly we rely on GPS clocks or GPS-driven or governed clocks, but each clock at a seismic station has to be calibrated so that we know how it performs within the world of GPS. The data management, there is not much calibration, but we need to understand, is it working well or not? Are we really collecting all the data that we want to collect? The telemetry is also important, particularly if you want to do real-time monitoring of earthquakes or nuclear devices. And then you have the other elements that I mentioned, the environmental elements that you have to at least inspect regularly in order to see, has the thermal insulation degraded? Is the styrofoam or whatever you use, is it still okay? Or has it gotten wet and suddenly changed its insulating parameters? And the tilt, I mentioned that earlier. So the bottom line here is only when we know all of these parameters, and really all of them, can we judge the state of health of a seismic station. And we can then, only then can we do the goal, that is measuring the ground motion with a high enough precision. So a couple of ideas, what we do in terms of field calibration. So there is, as we heard several times today already, there is the element of calibrating an instrument or a digitizer or a clock in the lab, but then you also want to know how these elements operate in the field. A simple test is the Huddle test, where you put many seismometers of the same type, you operate them simultaneously in a warehouse or whatever, and then you at least get information about how do these different instruments from the same manufacturer, usually, how do they compare to each other? That's the first simple way to find out outliers. We can also, of course, take lab-calibrated, seismometers calibrated in the lab and take them into the field and set them up next to an existing seismometer under test, so augment the seismic station if you want, and you compare the respective measurements. But this is an extremely invasive operation. You have to disturb the measurement because you're going into the seismic station and you open the doors of the vault. You have to, you see the steps of everybody walking around there. So it's a very invasive way of trying to see how the seismometer under test and its other, the other elements of the seismic station, how they work. The field calibration, it sounds straightforward, but there are lots of elements that one has to take into account. For instance, the reference seismometer, there's one saying in seismometry, the performance of a seismometer is not the age, it's not determined by the age of the seismometer, when was it built, but how often it has been packed, closed, thrown on a transport truck, and then driven to a station and unpacked and so on. Every time, these are very delicate instruments, every time you can have something happen to the seismometer, and mechanical vibrations and different environmental conditions determine its performance. Then, as I said earlier, the interruption of the continuous measurement by opening the vault and putting in other instruments there. And then the other point that many people don't think about is when you have a running seismic station and you put another seismometer there that is calibrated, how do you connect it to the rest of the world? Does it have its own digitizer? Does it have its own clock? So you are not only introducing a new seismometer into an existing station, but you probably also introduce a new data acquisition system, which with all the consequences about their calibration, what we talked about earlier. So,
Horst,
yeah?
2 minutes.
2 minutes, okay. So conclusion, for precision measurements, we need a stable state of health. That's the most important part. It's not so much how are the instruments calibrated. It has to be stable. And the calibration of a seismometer is only one element of establishing state of health. And I always view the calibration of a seismometer as an element of troubleshooting process in case the state of health deteriorates or changes over time. And as an example, and I think Nick mentioned that yesterday in one talk, but we in Berkeley, we use a non-invasive health check, and it's sort of an alternative calibration method. Because when you look at the picture, you see the seismometer, the broadband seismometer on the right, and then we always have a co-located accelerometer, which is this black device on the left. And we just wait for an earthquake, because we have enough in California, so okay. And then we take the measurements of both of these instruments and either integrate or differentiate, and thereby we get two wave trains that are supposed to represent the same ground motion in a coherent fashion because they are only a foot or two apart. And we check, do they give the same results? And if we do this regularly, without interrupting the measurements itself, because we just take the data and after the fact we differentiate or integrate, depending on what we do, we can find out if the state of health of the station has been stable or has been deteriorating over time. And that is, from my point of view, a possible alternative approach which is non-invasive. Okay, I think my time is out. Thank you very much.
Thank you very much. We have time for one quick question.
Yes, please. Sorry, I can barely see you here with the light.
Yeah, I'm Yuri Starovod from CTBTO. Over the presentation, it seems to me that you've been interchangeably using state of health and calibration. How would you explain what the difference between state of health monitoring and the calibration?
So when I mentioned calibration, I don't only mean calibration of the seismometer. I'm trying to help you understand that there are many more elements of a seismic station that need to be calibrated. So that's an individual process. How does a certain instrument, how does a certain digitizer work, and how does it perform according to the spec sheets of the manufacturer? The state of health is the performance of the whole station, the whole element of a measuring station. And as I try to explain, there are many different elements that can deteriorate or change over time, and you have to understand all of them in order to find out what the state of health is. So state of health is a more general term, while calibration is specifically geared to one of the elements of a seismic station.
Okay, thank you, Horst. I think we need to move on. If there are further questions, we do have a question session at the end of the workshop. So, but I need to keep on time so we give other speakers their full time to speak. So, time to switch technology now to hydroacoustics. So, I'd like to introduce Steve Robinson, who's going to talk about primary standards, traceability to the SI units, comparisons and validation.
Okay, welcome everybody. Nice to see everybody here this morning. So I'm going to talk about hydroacoustics. So can I have the next slide, please? So we're going to have 3 talks on hydroacoustics. I'm going to talk here about primary standards, and they're linked to the SI. I'm also then going to introduce some of the topics that you hear about in the next couple of talks. To do with dissemination of those standards, calibration of the actual hydrophones that are used in the ocean, and issues about doing in-situ calibration to those hydrophones. So when we talk about primary standards, the idea behind this is that we relate those measurements that we make in our particular physical discipline, so it's acoustics in this case, back to the fundamental units, the 7 base units that you can see listed there, which of course are all defined now in terms of fundamental universal constants, such as the speed of light, Boltzmann's constant, and Planck's constant, and so forth. In our case, we have the Pascal as the unit of acoustic pressure, which we define traceable back to one of these base units. Next slide, please. And so what we've got here is an illustration of the sort of the pyramid, if you like, of the national measurement system. So the way these standards are related back to the base units is usually through realizations of those units at national metrology institutes. Then you'll have traceable laboratories, which are traceable back to those NMIs, which do measurements of calibrations of instruments, in this case hydrophones. And then you have calibration laboratories or users in the field who are doing measurements which then can be traced through an unbroken link, links all the way back to those primary calibrations made at the National Metrology Institutes. And to validate those primary standards, we have a number of different ways of doing that. We compare different methodologies that are based on different physical principles, but we also validate them by comparison, by comparing the measurement realizations to the different NMIs. Next slide, please. Does that work? Okay, right. So this just shows essentially the same message again, just showing you we're talking here about the primary calibration, but ultimately you then have there's usually a secondary calibration method to calibrate the actual instrument, or in this case the sensor, the hydrophone that's used in the field. You would also want some kind of on-site calibration method which can check those calibrations in the field, because of course once the devices are deployed they may change their sensitivity. And we also ought to think about why we do this in the first place, why it's important to have calibration and traceability, because it's really all about the consequences for the data that you're trying to measure. So you may want to know the uncertainties on that data and the quality and robustness of that data, and that's usually because it has some kind of impact on what you're doing with the data. Perhaps you want to relate the measurements you're making to some thresholds for, say, noise pollution, or perhaps you want to evaluate the performance of the system so you can make sure it's still performing to specification, or maybe you're interested in the absolute amplitudes of these signals because it tells you something about the sources that you're measuring with your sensing system. So in the end, it's all about the impact on the decisions you make with the data you're using, but that traceability back to this primary standard, this primary benchmark, it provides this traceability that we describe in the field of metrology. So I think Ch2 has already mentioned some of this. So there are a number of international standards for how to go about doing primary measurements. IEC 60565 being the basic one. Most of the measurements done at the at kilohertz and even down to 250 hertz are free field measurements, so you're measuring large volumes of water. But at low frequency, we tend to use a different calibration method called pressure calibration, which I'll explain a bit about in a minute. And that's actually where traceability is weakest, because we haven't done some of these comparison exercises yet to compare the different standards. And so below 250 hertz, we haven't had one of these international comparison exercises to compare the primary standards. And there's actually relatively few CMCs, calibration and measurement capabilities, declared within the BIPM's database. So this is, and this of course covers the area of interest to the CTBTO, the area below 100 hertz. So this is an area where we're trying to fill in some of these gaps at the moment. So just to say a little bit about, before I describe a couple of the calibration methods that are used, a little bit about this pressure versus free field. What we really want is a free field calibration, because a hydrophone or microphone is normally used to measure sound waves, which are emitted by some source, propagate through a medium, and are received by a receptor, whether it be your ears or a microphone or a hydrophone. It's very difficult to do these kinds of free field calibrations at very low frequencies. And so what is typically done is we do something called a pressure calibration. So here we are inserting the sensor element, in this case of a hydrophone, into a small chamber, which is small compared to the acoustic wavelength, and then we introduce an oscillating pressure into that chamber. So there are no waves involved here. The wavelength is much bigger than the size of the hydrophone in the chamber, and we're just exposing the hydrophone element to an oscillating pressure. It's not really a sound pressure. And the pressure calibration is equivalent to a free field calibration, so long as the hydrophone is small and acoustically hard, a low frequency, so you're much smaller than the acoustic wavelength, and as long as it doesn't respond to pressure gradient or sound particle velocity, then you've got essentially a sensitivity that's equivalent to the free field. And because it doesn't sense the medium impedance at these very low frequencies, it's actually the same sensitivity in air as in water. So we can do a calibration in air, which is equivalent to water at these frequencies. So the IEC standard gives a number of different methods. Hydrostatic excitation is an interesting one. Essentially, that started by the so-called dunking method, where you move the hydrophone up and down in the water column. Even a small displacement of depth gives you quite a large change in pressure. So that's essentially the method, the basis of that method. There's also other methods, such as vibrating columns and traveling wave tubes. I'm just going to concentrate on two, purely because we have those two at MPL, so I can show them in more detail. One's a calculable piston phone, and one's a coupler reciprocity method. So the piston phone, first of all, here we insert the hydrophone into a small chamber. We then drive that chamber with a piston. The pressure that the hydrophone senses depends on the compliance of that chamber and the change in volume caused by the piston, which we can measure because we measure the displacement in that piston using a laser interferometer. So here the traceability goes back to the primary standards of length, essentially, dimensional metrology, if you like. Of course, in order to, so that we realize an acoustic Pascal, the Pascal using this, we, of course, to be able to disseminate that, you need to calibrate a hydrophone. So you basically have to make electrical measurements. So there is some electrical traceability involved, inevitably. The frequency range on this system we've developed which we developed in the EU Infra EV project, goes from below 1 hertz up to 250 hertz, and you can see some pictures of the instrumentation there. It's, we can calibrate hydrophones down, typically we only go down to 1 or 2 hertz, but this one goes down to 0.2 hertz. Slight, over which range the hydrophone is flat, invariant with frequency, except for a low frequency roll-off due to the leakage resistance and capacitance, giving you a slight high-pass filter effect. And we're piggybacking here on airborne acoustics. So the very first piston phone for microphone calibration was developed by Richard here, who's on the stage here, back at MPL in the 90s, and we've adapted this for hydrophones. It still has the same corrections, many of the same uncertainties that you have for microphones. It's no longer an adiabatic process, so you have to correct for heat conduction, and a number of the other uncertainties are related to electrical difficulties of measuring at these low frequencies. Hydrophones are very high output impedance devices at these frequencies. And this has all been published, and we've also done some comparisons, which I'll show in a second with other methods. So the second method I wanted to mention was coupler reciprocity. Again, this is because we have this system at MPL as well. Here we're doing the classic reciprocity calibration with 3 hydrophones. We're measuring electrical measurements of current and voltage on those devices, but rather than being in a free field, which is the typical way this is done, we insert them into a chamber and do the measurements as pressure calibrations. The difference here is we're fluid filling, filling with water, and this means we can pressurize to simulate depth in the ocean. And typically the range goes from a few hertz to a few kilohertz. And again, the compliance of the chamber is important. It's much more complicated to calculate that for a fluid filled chamber because essentially with a piston phone full of air, you can essentially assume it's all due to the air. You can't assume that with the water filled chambers because the impedance of the water and the chamber walls is not that different in magnitude. Here's some pictures of the system. We're actually updating our system at the moment to try and get to greater depths and also the uncertainties, and we're not happy with at the lower frequencies because of a number of the difficulties, electrical difficulties, but also the transducers we've got as reference transducers are not satisfactory in some ways, so we're in the process of redeveloping this. I think that Will Slater will describe the system they have at USRD in a little bit of detail in his talk as well. There are probably around 3 or 4 or 5 of these around the world. The USA, UK, China, Russia, and Turkey are the only laboratories I know that have a system like this. I explained we validate them by comparison, so this just shows some of the results of that. We haven't had one of these key comparisons organized by the Bureau of Weights and Measures consultative committee, but we have done some informal ones. These came out of the Infra UV project, so on the left, because we can calibrate a microphone in this laser piston phone, we calibrated one that had been done by LNE in France, another one that had been done by DFM in Denmark, and we also compared with TÜBİTAK in Turkey, their secondary calibration method, but each of the calibrations was traceable back to our own primary standards, so for us back to the piston phone, and you can see on the right-hand side the agreement between the 2 methods down between 1 hertz and 250 hertz. I just wanted to say a little bit before I finish on secondary calibration methods in a small chamber. So essentially here, the principle is much easier. You basically just expose the 2 hydrophones, the reference one already calibrated by a primary method and the device under test to the same sound pressure or oscillating pressure in the case of pressure calibrations. And then you measure the ratio of the voltages and you can calculate easily the sensitivity. The difficulty here, though, is that because you're doing secondary calibrations of devices that will be used in the field, you need to consider whether your calibration represents the performance of that device in the ocean conditions that you've got for deployment. And some hydrophones can show variations in sensitivity with depth and temperature. So here is on the left, I've got some examples measured from our coupler reciprocity, showing the variation with depth of a hydrophone sensitivity across lowish frequency range from 20 hertz to a kilohertz or so. On the right, you've got some measurements against temperature and depth, but they are at higher frequencies, but they illustrate the same principle. So they're outside our frequency range here, that kilohertz frequency, but they do show that hydrophones can change their performance with depth and temperature. So it's important to be able to calibrate them when you're doing the secondary calibration, at least, in terms of the environmental conditions that will exist during deployment. And the final aspect I wanted to mention was, so we've got primary calibration, secondary calibration before installation, but then you need to do some kind of in situ testing. And that's much more difficult for hydroacoustics than it is for seismic acoustics and infrasound, because it's difficult to access the measurement stations. Essentially, if they're on land, you can basically co-locate a calibrated reference device and measure simultaneously the measurements of on the reference device and on the sensor that's used on the station. You can't easily do that for the hydroacoustic stations because they're in the middle of an ocean 1,000 meters down, maybe close to an island, but not readily accessible. So I think yesterday, if any of you attended the session in the afternoon where Jan talked about some of the principles of in situ testing, he covered in a bit more depth some of these. You could use a calibrated source. The difficulty with that is that if you don't get close enough, the propagation uncertainties might add to the uncertainties of the calibration and make it less accurate. And also sources are it's more difficult to calibrate them as a function of depth than it is for a hydrophone at these frequencies. You can actually, if you could co-locate a hydrophone, you could then do the same kind of measurement that's sometimes done with seismic and infrasound. You could also even use natural ambient sound in the ocean to provide the signal. You could use a calibrated source as well. It doesn't have to be calibrated if you've got a co-located hydrophone. It just has to provide a sound field. But you could also use ambient sound, and that's been something that's been tried and maybe looked at again in the future. I'll skip that one. I just wanted to say something about the other kinds of checks that are done. I've just said that it's difficult to do in situ testing for the hydroacoustic system of the CWDO. But they do some checks. This is one example. This is an electrical check where they insert a voltage between the hydrophone element and the electronics, and they test the electronics. So it doesn't test the hydrophone element, but it tests the system. And this is done periodically, so those of you who use their data may have seen these kinds of signals in the recording sometimes. So that's a vital check for the performance integrity of the system, independent of the acoustic sensor. And we've also done some checks on the relative sensitivities. So here we looked at the relative sensitivities or the relative signals from the hydrophones in a triplet, and we did a kind of statistical filtering to look at only the lowest levels of background noise, and making the assumption that that came from distant sources. And we took the ratio of the signals and looked at how they'd changed with time from 2011 to the earliest data we had, and we found that they were very stable, apart from one hydrophone on one of the stations which had shown a change of about 1 decibel. So that only shows relative sensitivity. It can't show the absolute, but nevertheless it does give you extra confidence that the systems aren't changing. So just in summary, the primary standards provide us with this traceability back to SI units. There's some gaps in our metrology in that we haven't done sufficient amounts of the validation that goes along with that by intercomparing between the different NMIs. That is due to happen next year, starting in 2026, so that is in hand. One of the weaknesses is being able to calibrate at the conditions that exist in the ocean conditions, which isn't generally available from many laboratories around the world. I would say probably only a couple offer that, and not necessarily, only one probably in the frequency range that's of most interest to the CWDO. And finally, one of the big issues with hydroacoustics is this issue of in situ calibration, which is something that's being looked at, and we'll hear a bit more about that from the two speakers later on. So that's all I have.
Thank you, Steve. We've got time for one quick question, if anyone has.
Mario.
So, Mario Zampoli from the Hydro team. I work with John at CTBTO. Regarding the measurements with a co-located reference hydrophone, when you have a mooring of a certain height in the water, that's about, could be 1,000 meters from the seafloor or higher, that is going to swing a lot with the currents. So you never know where your hydrophone is, but you do know your hydrophone is a few meters below the float. And the floats can be detected with the side scan sonar at 500 kilohertz, 200 kilohertz. Over those distances, we've tested that one time, and they do show up really nicely. So you could maybe consider floating over the hydrophone location and over the mooring, and then trying to identify where it is, and then lowering the hydrophone down and keeping that in check, because the frequencies are so different that it's not going to interfere. Do you think that could be a possibility?
Yeah, I think that could, and I think the other two talkers will talk about possibilities. I was just trying to introduce it. If you remember in the, I think the question we need to answer is how close the hydrophone has to be for how long, if you're going to use ambient sound, for example. Yeah. I mean, I think I don't know if you remember in the infra UV project, we tried to have a look at Gabrielson's method, and we tried to simulate it by using real signals from the hydrophones and tried to look at how close you had to be for how long. And it did look feasible, but how you logistically arrange it, that's another matter. So.
But those frequencies, when you're within 10 meters, you're probably not so bad
exactly.
off, right?
Yeah, we separated the hydrophones and assumed they were 10 and more meters apart, and had to look at the difference it made. And it did seem feasible, but you need to, if you remember the Gabrielson, they hold it in place for a long time, and they look for the coherent signals between the two, and they reject a lot of signals when they're not coherent, and they leave them there for days and days. So whether that's feasible in underwater, I don't know.
Okay, thank you very much. Thank you, Stephen. Okay, so next we move to infrasound, and I'd like to introduce Dominique Rodriguez. He's going to talk about applying ISO 17025 and CTBT IMS requirements on primary calibration of infrasound sensors.
Thank you very much. Okay, so thank you very much. So I'm Dominique Rodriguez from the LNE, National Metrology Institute.
Closer to the microphone, please.
Yeah.
Thank you.
National Metrology Institute in France. So today, now I propose you to present a case study on how the international standard ISO 17025, which defines general requirements for accreditation of calibration and testing laboratories. So how we implemented this standard for a new calibration service provided at the LNE, which is a primary calibration of infrasound sensors. So despite this is a topic related to infrasound, it can be seen like a transverse topic also, which can interest the other fields. Okay, so first question, why targeting such an accreditation according to this standard? Such accreditation is, of course, more than just meeting a standard. It's a formal recognition of the competence by an independent third-party accreditation body. And I believe that this independent supervision is very important to build trust and credibility. Thanks to the ILAC also mutual recognition arrangement, this means that the accreditation is recognized internationally, and so the certificates, calibration certificates, can be accepted in quite all the countries in the world without the need to retest the equipment. It also means a direct alignment with the PTS EMS requirements, and finally, this ensures that the results are consistent, reproducible, and also, very important, fully traceable to the international system of units. So a few words first regarding the new calibration service. So it's a primary calibration of infrasound microphones by using the laser piston phone. It's a calculable piston phone. The core of the method is a rigid piston, which will generate a sound pressure inside a cavity, and this is achieved by the measurement of the volume velocity of the piston by using a laser interferometer, and also combined with an accurate knowledge also of the acoustic impedance. So currently we are covering the range of 10 millihertz to 20 hertz, and the method is fully compliant with this IEC technical report, which was developed just after the infra-heavy project. Okay, now the core of the presentation. So here, it's a general overview of the standard ISO 17025, as well as a very basic corresponding mapping with the current PTS EMS requirement for service provider, which are still in development. So you can see here in the legend this basic mapping. So the standard is divided into 4 main blocks. One first for general and structural requirements. So here to ensure that the laboratory is operating with impartiality, confidentiality, and has also a clear organizational structure. A block for the process requirements. So here, this defines how the laboratory operates from the initial request up to the reporting of results. A block also for resources requirements, here to ensure that the laboratory has the appropriate resources. And finally, a block for the management system, the clause 8, to ensure that the laboratory operates a management system that drives quality, consistency, and also continual improvements. So let me now show you how we implemented this. Oops. Okay, specifically for this new calibration service. So the first block, general and structural requirements, so very shortly, because here there is nothing specific to this new calibration service. This is implemented at the highest level in our organization. So for impartiality, the impartiality is enforced through clear policies, staff commitment, and when needed, escalation to an ethics committee. For the confidentiality, it is ensured by professional secrecy obligations, controlled access, and secure transmission of results. And finally, for the structural framework, Airline is, of course, a legal entity. We are responsible for our calibration services. Our governance is clear, and involve all the stakeholders. Our accredited scope is clearly defined also and limited. And finally, we operate under a unified quality management system, which is based in this standard, which applies in all the sites of the LME. And also, and this is very important, all the staff is responsible for keeping it strong. Okay, so the next block for resource requirements. So here there is 5 items. For the personnel, of course, we need a staff, a competent staff. So for the specific new calibration service, the operator is usually trained by first companion phase. So this companion phase can be less or more long depending on the profile of the operator. And anyway, at the end, the qualification is formalized, of course, and based with, on an objective criteria. So usually it's a comparison against an operator which is already qualified. For the facilities and environment, all the influencing factors are identified, of course. Some of them are controlled, like the temperature, but also the vibrations in this case. And for the other ones, they are monitored. Equipments and metrological traceability, I will focus just after on these 2 points. And finally, external service and suppliers. We need to, so they are carefully selected and approved, and we have to monitor them. So this is mandatory. Okay, so let me focus on metrological traceability and equipment. So the metrological traceability is necessary, of course, for any equipment that contributes to the validity of the results. So here, the measurand is the sensitivity, which is defined as a ratio between the output voltage and the sound pressure applied on the device. And so here, the critical equipment can be seen that those contributing to in building this basic unit. So here's the volt per Pascal. And so we have to link this basic Unix with the equipment which build these units. So, for example, the digitizer will provide the link to the volt. The waveform generator will provide the link to the second. The area of the piston will provide the link in part to the meter, and etc. So this is very important. So the metrological traceability means that all these equipments have to be calibrated, of course, by a service provider that can guarantee this traceability to the international system of units. So it's either an accredited laboratory which operates with ELAC accreditation, or an NMI which are the CMCs under CAPMMR. Okay, for the equipment, so close 6.4. So this is an example of how we manage equipment under this quality management system. So it is an example for the cylindrical coupling cavity. First, we need a procedure which covers handling, transport, storage, and planning maintenance. So this procedure is mandatory. And after that, we have to define the critical specifications for this device. So here in this case, the critical specifications are the dimensions, the radius and the height, because these quantities are necessary for the calculation of the acoustic impedance of the cavity. So then we have to define two things, the conformance criteria and the periodicity for the monitor these critical specifications. The conformance criteria, here is a dimensional drift, because we know by the calibration the true values, but it can drift in time. So we have to define a dimensional drift, which we define here 0.2 millimeters, which is reported in the uncertainty budget. So then, after that, we have to define the periodicity. The periodicity is a risk assessment, I will say. It's a balance between the cost and the risk. The cost to repeat unnecessary control of this calibration, and the risk that, in fact, the dimensional drift exceed effectively the conformance criteria that we choose. So it's a balance between these two things, and here in this case we choose 5 years, which is enough because the cavity is in steel, and the conformance criteria is quite large for this device. So it is managed. We maintain records for all of these, manufacturer fields, service history, of course, etc. We have safeguard with restricted access to the trainee staff only for the equipments, and also clear tags to know the status of the equipment. So, yeah, this is an example. We manage all the other equipments in the same way. Okay, for the process requirements, so here there is many items. This block, once again, defines how the laboratory operates from the initial request up to the reporting of the results, but including also provisions and requirements for complaints, non-conforming words, and data control. I just will focus here on 4 items which are relevant to, important for this new calibration service. So first, for the selection, verification, and validation of methods. So this is very important when implementing a new method. We have to do this first to be sure that we can obtain the performance we are claiming. So the 2 points very important here are verification and validation. So verification aims, in fact, to confirm that the method achieved the required performance and certainty, specifically. And to do that, we have several tools, but usually we use interlaboratory comparisons. So here, in this case, we participated in many comparisons under PTS, but also during the infra-UV project, but also internal comparisons at the LNE to cover some likes in the previous interlaboratory comparisons. For the validation, the validation is necessary for non-standard methods. So here, formally, an IEC technical report is not a standard, it's a technical report. So the question to know if we have to validate it, it's questionable, but anyway, we validate it because we started the project before the IEC technical report. So here also we have different tools to do that, but the stronger tools is probably a comparison, to provide comparisons of the results against other independent and recognized methods. So here we performed comparisons with other methods like the calibration of microphones by using a pressure reciprocity method, but also comparisons against static pressure sensor compared to comparison provided by a static pressure laboratory. Okay. Uncertainty measurements, of course, this is mandatory. So in this case here, we use the GUM, the methodology provided in the GUM. The GUM is a guidance edited and published by the BIPM, which provide a methodology in four steps. So nothing new here. So first, we have to identify all the uncertainty components. So there is many families are provided here. I will not detail. Measurement of sensor output, piston fan properties, etc., leading to the following best uncertainties, which are between 0.04 dB and 0.08 dB for the magnitude. It's important thing is that the uncertainties depend first on the frequency. We have larger uncertainties at lower frequencies, but also they depend on the sensor kind. So in our accreditation scope, we have 3 types of CMCs for 3 kind of equipments, like microphones for microbarometers, but also for barometers. Ensure validity of results. So this is a very important requirement also, but it's quite different than the verification and validation of the method. Here, in this clause, the standard requires that the labs monitor the results continuously. This is very important, continuously. And this to detect anomalies very, very early. So the usual tool to make this control continuously is also, once again, to participate to interlaboratory comparison, but here it's a planned activity. So we have a plan for that, and usually we have to make 1 interlaboratory comparison per cycle of accreditation. In France, 1 cycle is 5 years. But as the method is quite new, we implemented also another thing, which is a systematic evaluation of bias by using other reference standards. So for each calibration, we have always 2 reference sensors to monitor the results. 1 barometer to monitor the results at low frequencies, and 1 microphone to monitor the results at high frequencies.
1 minute,
okay. I will pass this tool. The last point, clause 8, so this is for the management system. We have 2 options to implement that. Option A, the laboratory has to implement all the clause from 8.2 to 8.9 with the score elements, or option B, the laboratory operates a management system under the certified ISO 9001 certified system. So LNE use option A. Okay, just to conclude, so this standard accreditation provides a guarantee, once again, of competence, impartiality, and international recognition of calibration of results. At the LNE, so our accreditation is derived by the COFRAC, which is also signatory of the ILAC MRA. By applying these standards, we are happy to participate into contribution to support the PTS EMS on the quality system. And I would like to finish this presentation by encouraging the collaboration. As you've seen, interlaboratory comparisons are very important. So I ask to participate on collaboration, but more generally also in method development and knowledge sharing. Thank you.
Thank you very much, Clement. So I think if you're not in the calibration business, this ISO 17025 standard may not be very familiar, but it really shows that there's a lot more than just having a technical solution to establishing a fully recognized calibration capability. And I think this is why the PTS, for example, are interested in quality assurance, because it brings all these other assurances with alongside the technical capability for doing calibrations. So I think thank you, it's very interesting talk. We got time for a quick question if there are any. No, if not, I think we can move on. Time is the master. So.
Thank you.
Thank you very much. Our next speaker will be Thomas Bruns, speaking on SI traceable laboratory calibration of seismometers with or without a laser. And I just want to remind everybody that if you're not here, are online and you're listening, or even if you are here, you can send questions through the S&T app and we'll find them and pick whether we want to ask them or not. Thank you, Thomas.
Yeah. Yes, thank you for attending this session. And my name is Thomas Bruns. I already introduced myself with a comment. I'm from the National Metrology Institute of Germany, and we are very busy with implementing seismometer calibration methods. So far, the technical solution, as Richard named it, we have a quality system in place, but we still then have to integrate seismometer calibration into this quality management system. So what I want to do today with this presentation is remind you of the laboratory calibration methods that are currently available more or less in metrology for seismometer calibration, briefly on primary methods, and then I would like to focus on some new results and experiences that we made for the comparison calibration. So first of all, a very short introduction. It was already told to you by my preceding presenters. What is a calibration? It makes a relation between a reference standard representing the quantity and the indication of the instrument. And this, typically for seismometers, the input is a velocity that we somehow have to realize. We also talk about the realization of the unit. And then the voltage output of the seismometer. So I'm deliberately taking off the digitizer here. We also work on digitizer calibration, but that's a completely different topic. And we distinguish primary calibration and secondary calibration. That was also already briefly touched. By definition, the primary calibration is a calibration where the reference is of a different kind than the device under test. Different kind can be or is not really strongly defined in the VIM, the vocabulary of metrology. But usually it's a kind of realization of the unit that is closer to the base units, not necessarily directly a base unit. And the secondary calibration just means that you compare one sensor to another sensor of the same kind. So here, for us, usually the primary calibration for motion sensors is done by laser interferometry. So the reference is a laser interferometer and the device under test is the seismometer. And the secondary calibration is just comparing a seismometer to a seismometer. Or you could actually discuss about that, but comparing an accelerometer to a seismometer, they are so close in kind that I would call that a secondary calibration, not a primary, but there may be people who see that differently. Okay, so primary calibration. For the laser interferometric primary calibration, there's a long-standing standard, ISO 16063-11, calibrating by laser interferometry, and this is just a sketch of the principle using a Michelson interferometer as a demonstration. They are not used often nowadays, but nevertheless, they are good to introduce the thing. You have the seismometer connected on a precision shaker table, as Horst named it, with a moving mirror attached to the table. And you have a laser interferometer So a laser source that gives you the beam that is divided into a reference beam that is reflected by a fixed mirror, and the measurement beam that is reflected by the moving mirror on the shake table, and they are superposed on the detector, and there you have an interference pattern, so you have a light-dark change on the photodetector when the moving mirror moves. And with that, you can actually calibrate or calculate the motion by calculating displacement, velocity, acceleration, and you have a primary realization. This is how it looks in reality. Here we have a seismometer on a 1.5 meter peak-to-peak shake table at PTB. And you see in the back where the green points are on this small rectangular front side of a device. This is the laser interferometer. It's a heterodyne interferometer, which is a little bit different, but that doesn't count here. And the green spots are actually the pilot laser. They are not the measurement laser. The measurement laser is infrared, so you cannot see it, but the green spots are reflections of the pilot laser here. And I'm always asked about the straps over the seismometer. They are just for security, because in very rare occasions this shaker has made unexpected movements, and we don't want to have this 20,000 euro device just dropping off the table. So they are not under tension, so they have no influence on the actual measurements. Okay, if you look a little bit closer at this primary calibration, it is directly SI traceable. The laser wavelengths gives you the length measurement. The time is given by the sample rate, and then you measure the voltage of the output of the seismometer with a traceably calibrated device, and that's basically all you need. It's very precise, stable, and reproducible, and we have very good and very long time experience with that. However, it has some drawbacks specifically for seismometers. It measures only exactly straight motion along the line of the laser beam. So your reference motion is only the component that goes in the direction of the laser beam. So it does not account for gravity disturbances. So if in low frequencies your shake table may have some bending, then you have some gravity influences. There are papers on that already. It does not account for dynamic tilt effects at higher frequencies. We will see that later. And it does not account for the position of the internal sensing element or sensing point, if you want to call it that. So what velocity is the seismometer actually measuring with its mechanical components internally. So for low frequency, we found that this tilt effect of the airborne shake table is really a problem, where you get dynamically changing gravitational influences. It gives you some deviation at the low frequency range, and you are better off if you use a tilt table for low frequencies. And we developed a specific method at PTB where you actually, because the tilt table gives you a very defined angular tilt, but it also introduces a trajectory where the seismometer is moving on the circumference of a circle around the tilt hinge. So we developed a method where you can actually compensate for both influences and then get very, very precise measurements at low frequencies for seismometers. You see the publication at the bottom. But it only works up to 2 Hertz, because after that, the whole system is not rigid enough for the higher frequencies and higher accelerations. But nevertheless, it's very reliable, more reliable than the laser interferometric method I showed you before for very low frequencies. So, but then we have what we call comparison calibration or secondary calibration, where we compare 2 seismometers. We don't have too many in the lab so far, so I can only show those and not a full bouquet. There's also a standard out there, ISO 16063, same theories, but part 21, which describes that side-by-side calibration for accelerometers. And if you do that, it's pretty simple. The equation is just that the sensitivity here, I'm talking about magnitude, but phase is simple in the same way, kind of. The sensitivity of the device under test is simply the sensitivity of the reference rescaled by the ratio of the voltage amplitudes that you measure from the two instruments that you set up side by side. And if you do that, for those two devices that I showed on the photograph before, you get this frequency response curve, which is nice, looks simple, smooth, and wrong. Because it's wrong, because we did that measurement on that shake table I showed before, and we used the laser in combination with this comparison setup. So we know the primary results for the same measurement, and the primary results for this measurement looks like the green curve. Well, they should look the same if they are valid calibrations. They don't, so something is wrong here. And if you add the manufacturer's information, you get this red curve. Yeah? We call this the theoretical curve because it's the equation from the manual that is applied here. And that looks also quite different from both of them. Here you see problems also in primary calibration, apparently. So what's happening here? That was the question that we followed over the last weeks before this, this event here. So this is very recent results. So we have this laser interferometric capabilities in the laboratory, and we changed the interferometer to one device that is called a rotational laser vibrometer. For us, in this case, it's basically a two-channel interferometer. So we are using it because it provides you two laser beams that come out in parallel with a very well-defined distance of the two beams of 25 millimeters. And we measured on the mirror that is mounted rigidly to the shake table, and you see a mirror also attached by rubber bands to the seismometer. So we also measured the motion of the seismometer. And by using the two beams and being able to use the average of the motion detection of the two beams and the difference of the two motions, we can actually calculate the sensitivity in terms of voltage divided by the average, but we could also determine the tilt of either object that we pointed the two laser beams to. And that was the purpose of the whole modification of the setup. And what we found were basically two effects. One effect was a shearing of the seismometer feed. Everyone who works with seismometers knows that the feet should be pushed or screwed into the housing as much as possible, and the nuts have to be countered, and you only use them for getting the seismometer level with as little elongation as necessary. But still, here the seismometer feet were all completely screwed into the housing and locked, and you still have a little bit of shear. So we found that on average, the amplitude of the motion of the seismometer was a little bit higher than the amplitude of motion of the shake table. The other thing that we found, and this is a thing that's a property of the seismometer, so it should be included in the calibration because it's a property of the instrument. The other thing we found was a tilt, but the tilt of the seismometer was the same, very closely the same as the tilt of the air bearing table. So apparently the source of the tilt was the air bearing table and not the seismometer, not the instrument. Well, this is a symbolic view what happens there. You can imagine that there are kind of air springs under the table that just tilt and at the turning points of the motion. So these were the two major disturbances that we could detect with the rotational laser vibrometer with the two-channel measurements. And if you look at this disturbance of the shake table, the tilt of the shake table, this is something that should not be attributed to the instrument. This is attributed to our calibration device, and we have to correct for it somehow. So what is the influence that we have there? In the comparison calibration, we have, if we use two different types of instruments, we have two different trajectories that they are following. If you consider the green point in the center to be the sensitive center, the spot or the height where the seismometer actually detects the velocity with its internal spring mass and feedback system. So they are following different trajectories. They have different velocities that they are sensing, so you cannot compare these sensitivities directly. You have somehow to take this into account. And you can do that if you have the proper information. Then if you knew this height of the sensing element or of the sensitive center of the instrument, you can correct for it. So this simple equation that I introduced before gets a correction factor. And here we made an approximation that the tilt angle alpha is proportional to the acceleration, because it's an effect that happens due to inertial effects. The mass times acceleration gives you a torque on the tilt table, on the shaker table. It's not a tilt. It's not supposed to be a tilt table, but it is in this case. We applied a constant there because we looked at the tilt in terms of amplitude of acceleration, and it had a very nice linear behavior. That's the background for that. So then you can apply a correction, and if you do that, actually you can apply two corrections. I don't want to go into the details there. If you make these corrections, then you get the red or the green curve that I display here. The blue one is the original primary calibration that was not yet corrected. So this is the wrong primary measurement for the high frequencies. Here's only the high frequency part from 1 Hertz displayed. And the red and the green are two kinds of corrections. Basically, the difference between those two kinds of corrections is the one is I approximate the tilt by a rectangular correction, a rectangular trajectory, and the other one is I calculate a center of rotation for those two trajectories and use the radius, which is varying with frequency, and use this radius for the correction and take the circumference of the trajectory. These are the small differences, and we are still looking at which one may be more suitable in the end. So but with this, we come very close to the theoretical curve. I still would like to know how the manufacturer, without all those laser interferometers, fancy stuff, got to the theoretical curve, but I believe it's pretty close. And I believe we improved our measurements, so I don't believe in the blue curve.
Thomas, 2 minutes.
Yeah, I'm very close to the end. This is the same if we change the roles. If we use the reference now as the DUT, the device under test, and the device under test that we originally used as the reference. In both cases, of course, different primary results come into play. And again, you see that this correction improves the results. So in summary, primary calibration with laser Doppler interferometry works well in the typical frequency range here from 0.1 Hertz to 20 Hertz or more if the sensitive center location is known. This is something that I would try to advertise for manufacturers in the room. Think about whether you can make this a specification in your data sheet. It will be very fundamental for good calibrations, primary and secondary. We need to know how far your sensitive element in the end is above the contact point of the feed. Dynamic tilt components are there and have to be taken into account. Then primary calibration using tilt, and the gravitational field works well from 1 millihertz to 2 hertz. So for very low frequencies, it gets better and better the lower the frequency is. Again, if the sensitive center information is available, or two measurements at different heights deliver, what did I write there? The sensitive center location, that's SCL. So additionally, so you can either take it from the spec sheet if it was there, it's not yet, or you can make measurements, subsequent measurement at different heights. And secondary calibration using a reference seismometer works well from 10 millihertz to 20 hertz if, again, sensitive center location is known, dynamic tilt components are taken into account, and a traceable calibrated reference seismometer is available in the suitable frequency range. Thank you.
Thank you very much, Thomas. We have time for one quick question.
Thanks. Just like to comment about the seismometer, the response of the feet being part of the seismometer response. Seismometers are often installed in different ways. Generally, the feet are removable, and often seismometers are buried in the ground or installed in boreholes and so on. So the measurement of the response without the feet, I think, is also an important parameter for a seismometer.
I agree, and we know that. So far we are dealing with vault seismometers in our laboratory. We have not yet experience with borehole seismometers. What we usually do in service calibrations for accelerometers, which is our daily business, is we ask the customers, how do you want it? How do you use the instrument afterwards? And if they have not a standard use, which fits for the standard calibration, we adapt our calibration. Sometimes we consult with the customer that they are using it wrong, but that's a different matter.
We have another question.
Thomas, thank you for the great talk. Just one point. The location of the sensitive center, whatever that is, it's not a center of gravity, it's maybe your definition. You are using what I've seen in the pictures, instrument of a certain type, which is the Galperian type, where it is very difficult to really understand where the sensitive center is. If you would use the other type of seismometers with the orthogonal, the classic orthogonal arrangement, you know exactly where it is because you have the points where the three components are sensitive, which is the center of the inertial mass of each of these components, and they are then pointing in the right direction. So it is an important question mainly for the Galperian type of instruments, but I don't think it's that relevant, or it's that unknown, let's put it this way, for the orthogonal types of instruments.
Yeah, it's relevant for all these methods, for all the instruments. Again, for borehole instruments, you probably have different heights and or different positions for the different axes. And with this tilt table arrangement, we also have a method to determine it. It would be interesting to know whether manufacturers who know the internals and have CAD software, of course, are able to give that information in the spec sheet. It just would be very helpful for calibration. Thanks.
Thank you very much, Thomas.
Okay, so our next talker is William Slater from USRD, from the Naval Underwater Sound Reference Division in the USA. And this time we're going to have a slightly different format. He's remote, online, but he's made a recording of his presentation, so we're now going to play that recording for the next 15 or so minutes.
Hi, I'm Will Slater from the Underwater Sound Reference Division of the U.S. Navy, or USRD, and we hold the national measurement standard for the underwater acoustic Pascal in the United States. We participate in international key comparisons to establish traceability to the international system of units, which we disseminate to government, industry, and academic customers in the U.S., largely through the standard transducers that we build and lease to customers. Our primary calibrations provide a direct realization of the underwater acoustic Pascal, meaning they don't involve comparison to any other acoustic reference transducer. We use secondary calibrations, which involve comparisons to our primary references, to then calibrate our transducer standards in quantity, which we lease to our customers. This diagram shows how traceability flows from the International Bureau of Weights and Measures through our lab via our transducer standards. In this talk, I'll start with a basic discussion of calibration at USRD. Then I'll show you two of our facilities used in calibrating the CT-BT IMS hydrophones, our low-frequency coupler and waveguides. I'll finish the talk discussing in situ calibration methods. USRD does not perform in situ calibrations, so I'll be comparing them with the standard methods we perform in our lab to highlight challenges and places where there's additional uncertainty. First, some basics. We characterize our projectors by their transmitting response, which is acoustic pressure generated per unit voltage or current. Similarly, hydrophones are characterized by their sensitivity, the voltage generated per unit pressure. In the lab, we test transducers in pairs, one projecting sound and one receiving it. A fundamental ratio in our measurements is the electrical transfer impedance between the pair, the voltage generated by the receiver divided by the current supplied to the projector. We can make these impedance measurements with traceably calibrated volt and current meters, but how do we determine the corresponding acoustic pressure? That is done using the reciprocity method, and that takes advantage of the property of a reciprocal transducer that it can function both as a projector and as a hydrophone. With a reciprocal transducer, the transduction properties cancel in the ratio of the transmitting response and sensitivity, which can then be written in terms of only physical properties of the acoustic medium and the boundaries. This ratio is called the reciprocity parameter. Here are two common forms of the reciprocity parameter, one applicable to free field in terms of distance, density, and frequency, the other to a small pressure chamber, which is in terms of the bulk modulus of the acoustic medium and the compliance of vessel boundaries. To carry out this method, you measure 3 electrical transfer impedances contained in this Z3 parameter. 2 driving with the projector and recording with the unknown hydrophone and reciprocal transducer, and the third with the reciprocal transducer driving and the unknown hydrophone recording. This ordering sets up the ratios required to form the reciprocity parameter and replace transduction properties of the reciprocal transducer with physical properties of the fluid medium and boundaries. We are left with the sensitivity of the unknown hydrophone without reference to any other transducer response, which is a primary calibration. Once we have a calibrated reference hydrophone, we calibrate other transducers by comparison, which is less involved. We can do a side-by-side comparison at low frequencies where we know the acoustic pressure is the same at the location of the reference and the unknown hydrophones. At higher frequencies, we measure the acoustic pressure at a point in the medium with our reference, essentially calibrating the projector. Then we replace the reference with the unknown hydrophone at the same spot. All these methods are found in IEC 60565, which also lists sources of uncertainty. And keep in mind that any uncertainty in the primary method propagates to the secondary method. There are many sources of uncertainty in the IEC standard. Here are a few. Uncertainty in voltage measurements, uncertainty in position, orientation, and fixturing. These are relatively small at low frequencies where the CT-BT hydrophones operate. And they also contribute both to the primary and secondary calibration. For the low frequency primary calibration, most of our uncertainty comes from how well we know the speed of sound in castor oil, which is our acoustic coupling medium, and how well we know the boundary compliance of our pressure chamber. To improve the state of the art in our lab, we're refining these estimates. We're building a device to measure speed of sound in castor oil more accurately. We are developing a new pressure vessel with an improved finite element analysis to understand its compliance. And we're also improving our voltage and current measurements. So these together should reduce our laboratory uncertainty. Here's the measurement uncertainty provided by our laboratory methods. Varies from about 0.6 dB to 2 dB. Notice the smaller secondary contribution to total uncertainty, which is smallest at low frequency. So any in situ methods using hydrophones calibrated at USRD will build on top of this uncertainty shown here. Now for a look at our low frequency calibration facilities. These are the facilities used to calibrate the CT-BT IMS hydrophones because they can simulate the temperature and pressure conditions at depth in the ocean. First, the pressure vessel where we calibrate the primary reference. It's a pressure chamber just large enough to house the 3 transducers for a reciprocity cal. A vacuum removes air from the coupling fluid, and a pressure ram and temperature bath control the hydrostatic pressure and temperature in the acoustic environment. Here are the components: the chamber itself, the voltage and current measurement system, the pressure ram, and the vacuum chamber. The temperature bath is under the table. With the primary reference calibrated, we perform secondary measurements in our waveguides, which are larger so that they can accommodate a variety of customer devices. In these diagrams, you can see a reference hydrophone or an array of references that facilitate side-by-side comparison. The customer devices, projectors. One of the waveguides has a projector just at the top, which sets up a standing wave. The others have them at both ends so that we can cancel reflections to make a traveling wave. In this picture, we're lifting the cover off the top, and you can see the projector and the brass rod that suspends the reference hydrophone at the bottom of the waveguide. Here we're about to open our horizontal waveguide. It's in this black frame, at the back of which you can see the tubes that circulate fluid through the chamber, the heaters, the chillers, and the vacuum. With the cover off, we can install and remove test equipment. So for this last section, how can we translate laboratory methods and their well-characterized uncertainty to in situ methods in the ocean? So I'll be providing some perspective on the challenges posed by the in situ calibrations I've reviewed and categorize and compare them with laboratory calibrations. Similar to our comparison replacement in the lab, at sea, a source like an air gun could be used along with a reference hydrophone to calibrate an IMS hydrophone. From the language of IEC 60565, this is a projector calibration using a calibrated hydrophone, followed by a hydrophone calibration using a calibrated projector. The repeatability of the source and the accuracy of the separation distance and hydrophone voltage measurements will contribute to uncertainty, as well as additional challenges. For example, correcting for source interference, separating the direct and reflected signals. An airgun survey at Ascension Island in 1999, conducted with a moored reference hydrophone, successfully characterized the repeatability of an airgun source and determined source to receiver distances within about 100 meters. This would correspond to an additional 0.2 to 0.8 dB of calibration uncertainty, that 100-meter distance uncertainty. A successful calibration could not be produced in this study because the unknown hydrophone was mounted to the ocean bottom where the direct path couldn't be separated from the reflections. But the IMS stations are moored in the water column away from the bottom or the surface. So this method might be viable, but a more rigorous uncertainty estimate is needed. Beyond the techniques used in the airgun survey reports, if geometric spreading cannot wholly account for transmission loss, like we assume it does in the lab, inverse methods could be used with a propagation model to characterize the true transmission loss. Similar to our side-by-side calibration, relative calibration methods in the IEC standard could be employed by positioning a reference hydrophone near the IMS hydrophone and recording ambient noise. Here there is no source to characterize, no distance to measure, no transmission loss to calculate, or direct path separating. It's just a comparison of voltages from the reference and IMS hydrophone. But the challenge is positioning the reference close enough to the IMS hydrophone so the sound field at each hydrophone is the same. This is easy in the lab, but difficult at sea. In an exploratory study, Harris et al. From the National Physical Lab in the UK showed that an ambient side-by-side method can work, but with degradation in the uncertainty of the calibration for separation distances of even just a few meters. This degradation can be monitored using the coherence of the signal from the hydrophones. But again, the coherence was adequate only at the lowest frequencies. Potential workaround. There's a method from Crocker that only requires a quasi-diffuse sound field and does not require coherence. It's extended a frequency range for one of our ambient methods to frequencies an order of magnitude higher. The uncertainty can be estimated using the data recorded during the calibration, along with adherence to the statistical requirements for the quasi-diffuse sound field. The drawback, as I've shown in this picture, it requires several references. And it was also developed for use in shallower lakes where sound speed variation and refraction can be ignored. So this theory would have to be extended to the deep ocean environment, and then practical considerations could be evaluated. The last method is an in situ reciprocity calibration that would require a new design of hydrophone to be deployed to the IMS. But note, this is not a primary calibration, even though it is reciprocity. In this method, a hydrophone assembly is built from 3 transducers. First, the hydrophone is calibrated in the lab by any method, and then it's built into an assembly with 2 projectors. At least one of the projectors must be reciprocal. Upon deployment, a reciprocity calibration is performed, except we know this hydrophone sensitivity, so we can solve for the unknown reciprocity parameter. From here on, the measured reciprocity parameter is assumed stable, which will be true provided that the properties of the water and the boundaries are stable. The hydrophone is then again treated as the unknown, and reciprocity calibrations performed with the assembly can be used to update the hydrophone sensitivity over the life of the hydrophone. An apparatus like this was built in the 1960s, but I have been unable to get any further information so far because the manufacturer is no longer in business. The patent file estimates for a transducer spacing of 7.5 centimeters, this device could operate down to 150 hertz. That's assuming ocean ambient noise of 110 to 120 dB. So implementing this would require sourcing transducers that could operate below 150 hertz, designing a reciprocal assembly and electronics, and testing it under controlled conditions to understand the uncertainty and how it might work in practice. This is how I would summarize these in situ methods. They're the comparison replacement like tests that use a source and a reference hydrophone have uncertainties much like in the IEC standard, but just larger and more complicated. There's more equipment involved. The side-by-side varieties use less equipment deployed at sea, but they have a new source of uncertainty because we can't enforce that the sound field's the same. But we can characterize that difference using statistical tools. And finally, an in situ reciprocity would require design and testing of an entirely new device. And thank you. That's the end of my presentation. Any questions?
Okay, thank you, Will. We're running short of time, but while we change over back to the presentation live in the auditorium, if there's any questions for Will, he is online on the WebEx link and may well be able to answer. So do we have any questions in the room? We don't have any online at the moment. No? Okay, well, if you do have any, you can save them up and make those questions available through the app, and then we'll pass them on perhaps in the discussion at the end, we can raise them and answer them then, okay? So thanks once again, Will. And now we move on to the next presentation, and I'll hand over to Peggy.
The next presentation is seismometer field calibration approaches, and it's given by John Merchant. Thank you, John.
Thank you. So I am John Merchant at Sandia National Laboratories, and we represent an expert laboratory that is able to perform evaluations and calibrations of the seismometers and infrasound sensors used in nuclear explosion monitoring. So we wanted to just provide some thoughts on some of the approaches for field calibration, and hopefully some examples of some of our research recently that you might find interesting. So, so why have traceable field calibration, and why are we having this discussion today? It's really being driven by the fact that such progress is being made in the National Metrology Institutes and the international agencies that handle the metrology, and that we have these capabilities now to make these measurements. And as far as why have it in the field, and it's really about making sure that the instruments are working properly. It's all well and good to be able to say that you know your calibration and your response to 0.1 or 1%. Does it make a matter for the geophysical instrument measurements you're making? Maybe, but it tells you something about the proper functioning of the instrument and allows you to ascertain when the instrument is not behaving properly, attributing why. And so those are important questions. And so really, we do these terms of environmental susceptibility and failure modes get thrown around. But really what we need is a process where we can continue to ensure the instruments are robust, are performing well, and we understand them through their lifetime. So I was just going to review just a couple of methods of doing field calibration that I've came off the top of my head. This is by no means exhaustive, but some things to reflect on. There's been some presentations by Thomas and others on these methods of laboratory calibration, and some people propose just send the instrument back and be rally calibrated, and really that's not a good alternative. It requires the instrument to be removed from service. It requires it to be shipped. That's very detrimental to the hardware, and we don't want to be doing that. So despite the fact that we have these great capabilities in the labs, they're in the labs, and they're not in the field where we need them. So one topic I've heard mentioned over years has been, we'll just compare it to another seismometer of the network. If you have an array, if you have another station close by, it has the advantage that you don't have to install anything, you don't have to disrupt the operational sensor. Oh, I'm sorry. All right. So, but it's very difficult to compare. So. The other stations are too distant, there's lack of coherence, there's poor SNR. And so I just highlight this example from Michaela Schwartz at a 2022 O&M workshop, where she was looking at elements of array and saw that, even at a very close distance of about, 1.4 kilometers, that the coherence was breaking down below 1 hertz, or, once you got above 1 hertz. And so it's really not suitable. And the other issue is that just really, it pumps the question of traceability to another seismometer that is also not calibrated. So it's a consistency check, not a calibration. Horst talked about this technique of performing a weight lift test. You put a mass, you expose the seismometer, it doesn't like that. You put a mass on top of its proof mass, pull it off, and you can look at things, and so you see these two plots of either the damped or undamped output of a seismometer when you've conducted a weight lift test. And yes, you can tell things about the free period, the damping, the in-band sensitivity, but it's very difficult, and these are hard missions to make over very short durations. And the other is that it's invasive. Horst mentioned that it takes an expert analyst to be on site, cracking open these seismometers to do this, and also, not really suitable for current, active feedback broadband seismometers anymore. So, we have the current method that's in use quite a bit today of electrical calibration. It's in place, it's well supported, we don't have to uninstall or install anything else. It only interrupts the operation of the seismometer very briefly while you're running the calibration signal. And so you would think, oh, hey, we're great, we've got this. But really, we've, just a personal opinion, we've entered an era of complacency and assumption that this is telling us what we need to know about the instrument. And hopefully we're not deluding ourselves too much, because you really can't distinguish between the characteristics of the electrical calibrator, the characteristics of the seismometer, these issues of the seismometer suspension, because you're actuating the mass and not actuating the case, and it's different parts of the mechanics. And as well, there's no traceability of the SI in this electrical calibration process. So it's an important tool, but it doesn't have traceability. And I'll even throw in, if you don't want to believe me about it, this is the Streckeisen STS 2.5 manual, and the highlights are mine. The exclamation mark is Streckeisen's. And they say, do not use it for absolute calibration. Let's see, it is a good state of health measurement, and anything that disrupts the feedback transducer, or a fault-inducing parameter, will not show up in doing an electrical calibration. So take that, as an engineer, that's a very concerning paragraph. So what's the answer? And we've been throwing this idea of these in situ comparisons. You put another seismometer next to it, and there's been discussions about, yes, you don't have to remove the operational sensor, but you have to put another sensor alongside it. And there's open questions about, is this a temporary emplacement? Is it something that's there permanently, or maybe only there for a few years and gets swapped out? Questions to be answered. But the principle of in situ comparison provides the mechanism to get a comparison seismometer next to it, not disrupt it, and have an unbroken traceability chain. I think the presentations yesterday and today on these topics are very relevant and pertinent, and are looking into the issues of these. But I think that's probably where this is moving in this direction. So now I'm going to switch chart tracks a little bit, and I'm going to show some examples of some recent work that we've been doing, performing both electrical and in situ calibrations, hopefully highlighting some of these concerns. So the first one I'm going to talk about is this assumption about knowing the response when you do an electrical calibration. And I have a great poster on it for tomorrow. If you want to see a lot of the technical details, please come find me. But really, just at a very high level, I've got these two plots on the left of amplitude and phase response. We took a seismometer, the same seismometer, connected it to different data recorders, and measured its response while connected to different data recorders, and then created a mathematical model for what we believed it based on the influencing characteristics of both the seismometer and the digitizer. And so the mathematical model are the solid lines on the left, and the dots are the measurements we made on a laser shake table. And we see that there's disagreements between the nominal, and there appear to be better agreements between some of these more complex models that the manufacturer left out poles. And so those things are in band, and they matter even though they're being disregarded. I encourage everyone to question the accuracy of the nominal models that the manufacturers provide. Make sure we check those things. But ultimately, if you do an electrical calibration with the wrong response model, you're going to be mathematically removing what you believe to be the responses for the seismometer and the calibrator. And if you assume poorly, you'll be left with a residual that's non-unity, non-zero. And so you can see these two plots on the right now. The topmost one is just using the generic seismometer nominal model. And you can see that there's a phase residual. And I've highlighted the section where it actually exceeds the 5-degree requirement for IMS purposes. If we use a model that has additional poles that were left out by the manufacturer, then they correctly account for that residual, and we're left showing that things are right. So the takeaway, I guess, would be the electrical calibration is only as good as the assumptions that you made before you did it. So the next example I'll show are some cases where we did some work with looking at the temperature effects on both electrical calibration and in situ comparison. And this was really motivated by Nick Ackerley's work from S&T 2 years ago, where he was looking at the effects of temperature at Yellowknife on S13s. And we wanted to try and do something similar. So we, at one of the installations at our facility, we installed temperature probes on a GS13 and a CMG3T seismometer. And then we proceeded to run a 1-hour broadband electrical calibration every night for a year. And so we ended up with a fairly large data set of comparisons between the voltage signal into the calibrator, the output of the seismometer on those two instruments, And then we took the additional step of doing in situ comparisons between the measurements of ground motion between the GS13 and the CMG3T. We took advantage of this PTS CalXPy tool, which helps find time periods and frequency bands of coherence and assemble it into a usable representation of the response, and gave us some metrics of how much these parameters are varying over the 1 year, with where we see this temperature variability of approximately 25 C at our facility over this year. And I should say that's 25 C on the seismometer case, not the outside. So what did we see? So here are the results of looking at the variability and the electrical calibration for the GeoCheck GS13. We have plotted on the right. The top plot is amplitude versus amplitude versus temperature, and the bottom plot is phase versus temperature. And we see this very clear, high SNR, low variability fit to a linear function, where clearly there's a linear relationship between the amplitude at 4 Hertz and the temperature of the seismometer. So there's this temperature dependence, and based on the models from NRCan that we were able to utilize and adapt, it actually matched really well. So this was a good confirmation. And if we expanded that and we looked at more frequencies, we ended up with something that was very frequency variable. There's a table of the amplitude and phase coefficients at a couple of different frequency points. But you can see that it's, especially around the corner frequency, there was a lot of change. The similar plots on the right, we tried to plot the amplitude and phase as a function of frequency with different lines, and you can see that there's spreads at different temperature points, indicating that under certain temperature ranges, you're at risk of having your electrical calibration not be within IMS requirements. So there's concern, both on maintaining stable temperature, but also on just understanding this from a perspective of wanting to know what the instrumentation does. So if we look at the results of doing the same electrical calibrations nightly on the CMG3T, we end up with a very different plot. Same, amplitude versus temperature for both, both amplitude and phase versus temperature. But there's no apparent change, and you might say, oh great, that's a great sensor, wonderful. Remember that STS 2.5 plot I said? This is an active broadband seismometer, and we're running an electrical calibration by injecting current into the feedback coil that it's then using to correct and sense, and so we actually believe that it is canceling out the temperature effect when you run the calibration. It's not invariant of temperature, it's just hidden from you when you do this electrical calibration. So what this would mean is this instance is that you're running this periodic electrical calibration and you're not seeing the true performance of the instrument because it's varying with temperature, and yet this method of calibration isn't showing you what you think it's showing you. So we're not seeing the true performance of the instrument. And that's further compounded when we use the CalXPy results from comparing the GS13 to a CMG3T. So we're taking advantage of just the natural background seismicity. It's everything. It's the microseism, it's earthquakes, it's local regional teleseismic sources. And we look at these periods from CalXPy where there was high coherence and try and plot them versus temperature, and you see, first off, it's not this great SNR signal that you would seen in the electrical. There's noise, there's scatter, it's less repeatable. And again, remember that this is now the lumped performance of both the reference, that we use the 3T as the reference and we use the GS13 as the sensor under test. It's both of them. And the earlier models for temperature variability that seemed to work very well on the GS13 for electrical calibration were off. in this case. Given that we had modeled the GS13 so well, we thought we had a handle on it. It was off by about half. And the only explanation we can come up with is that the rest of it is attributable to the 3T, but we just couldn't see it in its electrical calibration.
John, 1 minute.
Perfect. So with that, so my table of points, I'm not arguing against performing electrical calibrations. I think they're a useful tool. From time of installation, they can give you an indication, a state of health indicator, that likely things haven't changed, but that they're an incomplete tool. And something more is needed to fill that gap, to be able to tell what the environmental susceptibility effects are for the instruments that are the measurements they're making, that has traceability. And it's necessary but not sufficient. And so some of the questions I think that we still need to answer, is how exactly can we propagate this chain of uncertainty from the laboratory measurements to these field environments, taking into account all of these unknowns about environmental susceptibilities and the performance of instruments in the face of dynamic environments. And hopefully the work that we're all doing will help to continue to answer those questions and move us in the direction of understanding the instruments better.
Thank you very much, John. Do we have any questions? Yeah, please, Nick.
Thank you, John. That's a really wonderful talk and great work that you're doing. I have a question and a comment. I'm going to ask them both and then leave the mic. The question is, have you tried to fit poles and zeros to the response that you're getting in the electrical calibrations from the GS13 and look at how the poles and zeros vary with temperature? And the comment is that I really appreciate the approach that a lot of people in this room are taking seeing the seismometer as a black box. I think that's the right rigorous approach in a lot of cases. But when designing calibration processes, I think you need to take a little bit of a peek in the box and see what kinds of tests probe which components in the box. And I think that's one thing we're running into here. You see it in the STS 2.5 manual that the electrical calibration specifically doesn't probe certain parts. And so that means that other methods, in my view, not that you throw away electrical calibration, but that you investigate complementary methods that specifically probe those parts, namely the force feedback transducer. So that's my comment.
No, I think, thanks, Nix. I think those are great comments. So the first one, I think we've been focused right now on just making the measurements and having the tables of FAPs. So no, we haven't tried yet to fit the poles and zeros, but that's a great suggestion. And I think for your comment on the black box, I wholeheartedly agree that our base approach for testing is to approach from a black box perspective. But often what we also find is that once we have those results from black box testing, trying to understand the why of them requires investigative probing into looking into what the design is, conducting subsequent tests, try to tease out what are the contributing components in that design that led to that, so that we can understand the why of it.
Thank you very much, John.
Okay, we're moving on to another hydroacoustics presentation now. This is by Silvano Buogo, and his title is Exploiting Low Noise Spectra in a Natural Lake for Free Field Hydrophone Calibration. Silvano is online on a WebEx connection, so he should be able to present the presentation live. So over to you, Silvano.
Can you hear me?
Yes, we can hear you.
Okay, thanks. So thank you for inviting me to this conference. I also thank session chairs and especially Chan, who has invited me to give this talk. I assume I should share my screen. If not, just let me know so that I just wait for the slides to show up on the main screen.
Can you show his talk?
It's probably easier for you to
Can we show the talk
my
here,
slides.
and then and on the online, and then Silvano can just say next slide. Is that possible?
Exactly. So, good. So I am Silvano Buogo from the Institute of Marine Engineering of the Italian National Research Council, and I'm presenting this work to you together with Fabrizio Borsani, who is from the Italian Institute for Environmental Protection and Research, and also our PhD student, Valentina Caradonna, who is from the University of Campania Vanvitelli. Now, the motivation for this work, okay, the slide overview, thanks. The motivation originates from two projects. A regional project that ended last year, and this was essentially a follow-up of a previous Euramed metrology project. And a second project that's ongoing that has to do with deployment of autonomous recorders in the Adriatic Sea. And in these two projects, we worked on defining a new setup, simplified setup for free field calibration of receivers, both hydrophone and autonomous recorders, to be implemented in a lake. As we have access to a lake near Rome that's located, as you see here, Lake Bracciano. It's a volcanic lake about 30 kilometers northwest of Rome, has about 8 kilometers diameter, and is about 165 meters deep. So it has nice characteristics for many reasons. First, of its size. Then also for being inside a regional park that has strict rules on the preservation of the ecosystem. So any man-made activity is strictly forbidden except permitted work. And so this works on our side because we are really able to have pretty nice conditions, as you see from the pictures on the right side. In the morning, normally, the water surface is flat with basically no wind. And this creates a very quiet environment. So we exploited that, and apart from performing the calibration using a variation of a traditional comparison method, we also took a look at the ambient noise data, and that's the topic for this talk. So next slide, please. Now, I will not give you much detail on the setup that we used for this calibration because it's being described elsewhere, it's being published elsewhere. But it is essentially a variation of a classical comparison method where the source and receivers are just deployed using two very near lines. As you see from the picture, the source is deployed at a variable depth between 1 and 6 meters, and below the source there is a receiver, which might be either an autonomous recorder or a hydrophone, standalone hydrophone, with a reference hydrophone co-located. Our reference hydrophone was our second line standard, so it has a rather wide uncertainty, but that was just for field calibration. And due to this particular setup, we could exploit the free surface reflection in phase, so that at the receiver, we got a single arrival in phase, and then the first reflection happens at a much later time, about 125 milliseconds later, so that at the lowest frequencies that we investigated, that was 63 hertz, due to the requirements by the Marine Strategy Framework Directive, at that frequency we still got about 8 cycles using standard gated burst tone technique. So next slide, please. All right, so what you see here are raw data, unfiltered, starting from the lowest frequency, 63 Hertz, and middle frequency, you see the pulse shape is clearer. We used a rectangular shape with tapered leading and trailing edges. And the pulse length was about 130 milliseconds. Then at the right, you see what happens at higher frequency. At higher frequencies, this on-phase summation of free surface reflection does not work well anymore. But still, in the first portion of the pulse, you get the direct wave arrival only, which still has a sufficient number of cycles inside, so that a robust RMS detection can be still made in that early portion. So next, please. All right, a word about the source we used. We did not use a, let's say, classical piezoelectric transducer, but instead we used an electrodynamic underwater speaker that's based on a moving coil mechanism. It's essentially as a standard air loudspeaker, but it works in water. And the active elements are 2 opposite carbon fiber membranes that work in parallel on 2 half spaces. The advantage of using this source is that when you are on a small vessel and you have issues about security, safety, compact size, then the driving voltage for this type of source is really low. It's less than 20 volts RMS, which is much lower than it would be necessary using in these frequency ranges, using a piezo transducer. That's over a kilovolt. So this simplifies much the operations on board. If you combine the source to receiver distance that is in the range between 9 meters and 14 meters approximately, from the TVR curve that you see here that peaks at about 145 dB as in most traditional piezo transducers, but at 100 Hertz only, then the subpressure level at the receiver is in the range between 125 dB and 145 dB, which is a decent level. So next slide, please. And this is the core of our work. What we took is the blank, we call, so the ambient noise in absence of transmission with no noise sources at the best environmental conditions in Lake Bracciano. What you see is a fairly regular curve with sound levels that range between about 80 dB around 10 Hertz down to a flat portion of the spectra that's around 50 dB, but that's because the audio files were recorded using 16-bit format only, so that's mostly due to quantization noise. The dashed curve is what one would get if there were no hardware high-pass filtering, which was present in our measurement chain. So it's an idealized extension towards lower frequencies, starting from approximately 10 Hertz. But from 10 Hertz upwards to the tens of kilohertz range, those are just raw unfiltered data. So next, please. Next slide, please. Exactly. So this is the same spectrum that is evaluated using the same measurement chain, same hydrophone, same instrumentation, but in an indoor laboratory tank. And you see the difference in terms of presence of tonal components in at least in the decade between 10 Hertz and 100 Hertz, but even beyond that. And this is due to the presence of a number of unavoidable sources like machineries, fans, electronic devices, and even road noise from around the tank building. So the difference is quite visible. Here, there's one feature that is not easy to understand. It's the sudden cutoff below 10 Hertz. If one removes the high-pass filtering, hardware high-pass filtering at 10 Hertz, one still gets the dashed line, but that's not quite easy to understand. It's probably because the tank itself, due to its size, which is, well, the dimensions are between 4 meters and 6 meters, is not big enough for any sound field to develop below 10 Hertz at all. But this is, we are still working on the explanation of this. Anyway, this is of little practical use because a finite size tank is never used for such low frequencies. So next, please. If one takes the two spectra you've seen so far and takes the difference, you get the advantage of being in a lake environment towards tank, measuring tank. And you see that from 10 Hertz up to a few hundred Hertz, the advantage is clear. You get at least 10, 15 dB. And for those frequencies corresponding to the tonal components that you find in the tank, in the indoor tank, the difference is even more, it's even up to 30 dB. About the portion of the curve below 10 Hertz, again, this is of no practical use because the sound spectra in the tank below 10 Hertz is abnormally low. So next, please. This is essentially the same difference plot that you've seen in the previous slide, but only evaluated in decade delta frequencies. So it's much more regular and it's easier to evaluate it. So again, you get from 10 Hertz up to a few hundred Hertz, you get 15, maybe 10 dB advantage. So the lake is at least 10, 15 dB quieter than an indoor tank. So next, please. One word about signal-to-noise ratio. If one takes the figures that you've seen so far, what you get is the signal-to-noise ratio and the calibration that was described so far. It's a pretty good signal-to-noise ratio. It's at least 40 dB and even peaks up to nearly 80 dB at 100 Hertz. That's mostly due to the transmit characteristics of the source that we used. That's a very particular source that has a peak response around 100 Hertz, but eventually below 100 Hertz starts to roll off as it is combined with an electrical filter that's inside the body to prevent damage to the unit. So it's essentially a technological limitation. But again, looking at the overall signal-to-noise ratio, the lake exhibits a quite interesting characteristic. Next, please. I think that, yes, this is the last slide, so I was able even to catch up with time. And the conclusions are that I showed you the first results of evaluation of ambient noise in a lake that was used for free field calibration of autonomous recorders in the frequency range from 63 Hertz up to 20 kilohertz. Why 20 kilohertz? Because we wanted to have some overlap with standard tank calibration that's normally performed from the kilohertz range up. That is the only reason for extending up to 20 kilohertz. This lake we used as interesting for its very low ambient noise, especially between 10 hertz and a few hundred hertz. And the signal-to-noise ratio that was possible to obtain using the setup was pretty nice, at least 40 dB in the entire band. One last word I would add that's not written in this slide is that this lake, this say in situ location could be used favorable even for lower frequencies, possibly down to 1 hertz, provided that the measuring instrumentation is set up correctly with high-pass filter cutoff compatible with the frequency range of interest. I think this is all. Thank you for your attention, and I'm open to questions.
Thank you, Silvano. While we change back over to the the projection system in here, are there any questions for anyone to Silvano from the audience? We don't have any online. Okay, well, we're just about on time. So thank you, Silvano. We have a question and answer session at the end, so maybe people will save some questions up for the final session. So we now move over to the final talk and over to Richard.
Yes, so it's back to infrasound, where it's arguably the one that's most developed in terms of field calibration. And therefore it's appropriate that our next talk from Samuel Christofferson considers the uncertainty propagation in terms of transferring traceability from the laboratory to the field. So this is a kind of next step on from some of the things we've been thinking about so far for other technologies. Thank you, Samuel.
Okay, thanks for the introduction. So yeah, like Richard said, I'm going to be talking about infrasound uncertainty propagation, so ensuring that traceability from the laboratory and primary calibrations to the field. And this was done as part of the Infra AUV project, which was a project on metrology for low frequency sound and vibration. And my contributions were in sort of this working with incorporating these on-site calibration methods and into the full measurement traceability. So this is just kind of a schematic showing the basic idea of metrological traceability. So we have our various levels of calibration, starting with primary, secondary, and they've been discussed a lot. And we have also what I've called here field calibration, which is using sort of a traveling reference calibration. And also in situ calibration measurements. This is like the Gabrielson method of calibration by comparison. And then I think one other thing that I wanted to sort of take it a step further is look at, well, often with infrasound stations, of course we're interested in a measurement of pressure in pascals, but also we're often interested in, okay, what's the direction of arrival of an infrasound wave? And so for that, we want to see, okay, well, what's the back azimuth trace velocity and so forth. And so then what are the uncertainties that would be associated with those measurements, azimuth trace velocity, associated with calibration. And for this presentation, we're sort of going to focus on those bottom 3 layers of that pyramid. And so just to give a kind of quick overview of the wave parameter estimation, we used the progressive multi-channel correlation algorithm, which is basically a time delay of arrival method. So you've got imagine a wave passing across our array, and basically by measuring the relative arrival times at each sensor, we can make a determination of what the direction of arrival azimuth trace velocity. But you'll of course obviously note that since it's based on the time of arrival, then that means it's going to be sensitive to phase errors. So if there's phase errors or phase uncertainties, those are going to show up as errors or uncertainties in our wave parameter estimates. And so I guess comprehensive for this study, we looked at a comprehensive uncertainty budget, incorporating things like the three main sources being the estimation method, so that's our propagation model, the TDOA at PMCC, instrumentation, so that's sort of our array itself, the array design, the sensors themselves, so the calibration, as well as the sensitivity to local environmental conditions. And then there's also the incoming signal. So for the purposes of this, that's going to be dependent on atmospheric conditions, so how the infrasound propagates through the atmosphere and how it refracts and reflects and that. So for purposes of this, we're going to just say, okay, well, that's complicated, and once it arrives at the station, we aren't necessarily concerned with, at that point, how it's traveled through the atmosphere. So we're just going to say, okay, when it gets there, crosses our array, what are the impacts of these sort of instrumentation and our propagation model? And notably, I'm going to talk a bit about the effects of making a 2D versus 3D assumption with the propagation model as well. Okay, this stopped working. Can we get the next slide, please? It's not responding. Okay, thank you. So for this, we basically have four contributions to the uncertainty budget. We've got our field calibration, which is with this reference microbarometer SMIT. I'll describe it in a second. Our in situ calibration of the operational sensor using a Gabrielson method. And then we made assumptions on a position uncertainty of about 15 centimeters in the horizontal and a meter in the vertical, as well as our sensor susceptibilities to ambient temperature and pressure. So the SMIT, Système de métrologie infrasonnaire de terrain, so it's an in situ infrasound metrology system. Basically, it's so if you look in this picture, the sort of metal cylinder is the SMIT, and it basically is a sealed cylinder with a loudspeaker that generates an infrasound signal. And what we do is we have so you can see kind of see in that picture a reference microphone that's attached, and we can connect our microbarometer and then do a calibration relative to this reference microphone, which has been calibrated. And the idea there is, of course, then we can calibrate this microbarometer in the field in the ambient conditions. And now we have a microbarometer that is traceable to our primary calibration. And then we use that microbarometer as a reference for the Gabrielson style on-site calibration. And so basically that reference microbarometer is placed next to the operational sensor, which is connected to a wind noise reduction system. So this Rosette style wind noise reduction system. And then by doing a basic calibration by comparison with this calibrated reference sensor, we can now have the response, determine the transfer function of the sensor under test, the operational sensor. And so just overviewing the complete calibration chain, we have our starting with figure A in the top left. We have our reference microbarometer SMIT calibration. So we've got an amplitude and phase with corresponding uncertainties. Then we have the operational sensor calibration. And then there's a position, altitude error, or uncertainty. And so that is an effect only in the phase. We're assuming that there's going to be no impact in the amplitude, or pardon me, in the amplitude. And then we have our microbarometer susceptibilities and wind noise reduction system susceptibilities to the ambient temperature. And for the microbarometers, we only had susceptibilities in amplitude, so not in phase. And then the approach here to get our measurand, so our azimuth and speed uncertainties, was to basically take raw signals, and then we would apply the transfer functions. So basically take the Fourier transform and then apply the transfer function. So this big box labeled transfer function, you can basically just think about it, that's essentially this stuff here. So we would sample each of these different transfer functions or responses within those uncertainties randomly, and that would give us our transfer function for that run of the Monte Carlo simulation. We'd then get our deconvolved signals and then apply our time delay variable PMCC method, get azimuth and speed. Do that for n runs, 100,000 runs, say, and then we can get an average and standard deviation to get an idea of what the uncertainties are associated with the calibration on our measurement parameters. And so this is showing the results of those tests. So on the bottom we have the uncertainties corresponding to each different element of the calibration. So for example, in the azimuth and speed, to the left and the center, we can see that the effects of the Gabrielson calibrations, the on-site calibration and the Schmidt calibration phases on the uncertainties, as well as small uncertainties due to positions, but these are essentially negligible. The top shows us the Sobel indices, so basically that's going to give a relative proportion or importance of each different calibration or position uncertainty, each of these uncertainty sources on the overall results. So we can see for the azimuth and speed, these are dependent largely on the phase and not on the amplitude. So these are the largest contributors to the uncertainty are going to be the Gabrielson on-site calibration as well as the Schmidt calibration. When we start talking about the amplitude, we now see that there's impacts from still those two calibrations, but we can also see that the susceptibilities of the microbarometers are becoming important as well to the ambient temperature and pressure. So that means that the temperature and pressure in the amplitude, we didn't have that for the phase, but that means that those things are important relative to what we to the calibration themselves. And I'll just note too that, because it may be hard to see some of the numbers, but these uncertainties aren't huge, so don't get like looking at it and go, okay, the Gabrielson calibration is almost 1 in the Sobel index. It's large, huge values, but then when you look at the actual contributions, so for example at 1 hertz, we're looking at about 1/10 of a degree in uncertainty. So it's still not, these aren't huge contributions, but when we're only taking into account these calibration uncertainties, those are the most important ones. So now we'll just quickly talk about some of the effects of 2D bias. So with IMS stations, we often assume that these are planar stations, but that's not always the case. So for example, at IS-26 in Germany, there's over 100 meter or about 100 meter difference between the highest and lowest elevations of the elements. And when we take that into account, we can see in the figure on the right the impact or the biases, the errors that would be introduced by failing to take into account this three-dimensional nature of the station. So essentially, we could have azimuth errors of up to a few degrees, depending on the incident angle, and 10-20 meter per second uncertainties or errors, pardon me, in the trace velocity. And so these biases will, they do increase with increasing incident angle. So basically, if you have a wave that's propagating completely horizontally, there won't be any impact, but as the trace velocity increases, so as the angle increases, then that starts to become more important. And so just to kind of summarize all those results, we can look at sort of the total uncertainty budget, and the solid lines, we'll focus on the solid lines on those two left graphs first, and those are showing the Monte Carlo uncertainty, so all those calibration uncertainties combined, plus I added the uncertainty associated with signals-noise ratio of, for blue it's 20 decibels, orange 10, and green 0 decibels. And what sort of want to point out here is that with for these Monte Carlo calibration uncertainties, we can see that basically once you start getting less than a signals-noise ratio less than about 10 decibels, which is a pretty high signals-to-noise ratio, the calibration uncertainties are almost negligible compared to the noise. So essentially the signal-to-noise ratio is still going to be the biggest challenge in terms of infrasound. The other thing that is worth pointing out is the dashed lines are when we take those solid lines and then add the bias introduced by the 3D versus 2D, or the 2D bias essentially. And so even at 0 decibels, we can see differences between those lines. So that means that there are potentially situations at stations where we could have signals that would be biased if we're not taking into account the 3D sort of orientation or 3D nature of, three-dimensional nature of these stations. And I wanted to just show one last thing to kind of talking about all the uncertainties that are being added by, let's say added is not the right word, but all the uncertainties associated with calibration. And I wanted to just show an example of some real added value of doing these calibrations. Aside from just having, okay, well now we know that we have a measurement that's in pascals and all that, and that's all great. But what happens if, say we have a sensor that's defective? So in this case, I'm showing an example of IS-47 in South Africa during the Hunga-Tonga eruption. And one of the sensors at that station at that time there was a loose screw or vent or something. I can't remember exactly the details. But basically it caused a drop-off in the response in low frequency. And we can see the result when we apply to the figure on the left with the raw signal. We can see that we can see biases start to show up in the trace velocity notably, and then we get sort of a gap in that low frequency measurements of the azimuth trace velocity and our amplitude. And I think what's interesting or profound or added value of the calibration is when this station has a reference calibration co-located with the sensors under test. And so I was able to use those calibrations, apply them to the signals, to deconvolve the signals with those calibration responses, and then we get the figure on the right. And we can see now we're filling right in all the way down to the 0.01 hertz. Our azimuth and speed, we're no longer seeing those biases show up. So basically it is a great example of not only can we use this to sort of monitor the stations, these in situ calibrations, but then also in the event that something happens and you can't immediately fix it, well, we haven't lost that data. We can now still use that data and get accurate results. So overall, just to conclude, then we can see the calibration uncertainties are generally less than uncertainties associated with SNRs of about 10 decibels. If we failure to take into account 3D nature of stations can result in measurable, non-negligible biases in the results. And again, as I had mentioned in the last slide, calibration curves, this on-site calibration reference can be used both to monitor station health and to correct for in post-processing for defective data. And further research, I think it would be interesting to do further research looking at the phase susceptibilities of the microbarometers as well, because that would have an impact on the wave parameter estimations. Thank you.
Okay, thank you, Samuel. Does anyone have any questions? I don't see any.
There was one.
Oh, okay, thank you.
Hi, just a quick question. When you're sampling those FFTs, do you assume that the values at different frequencies are independent?
Yeah.
Is that based on like experience? Because I can also imagine, because there is a corridor there that, you know, it's tilted on one way or tilted another way, that there is a bias, like a systematic bias in those.
Mm-hmm. So you mean like these figures here? So I guess the one could, and we thought about doing it in different ways, and one of the things was to sort of have it be like almost like the whole thing shifting up and down or something. But then ultimately decided it's probably better to just say, okay, well, when we do the calibration, we say, okay, well, we know that we have a value within that range, but we don't know necessarily that it's all moving up or down together or anything like that. So it felt like a sort of safer estimate to decorrelate all of the frequencies and just say, okay, well, we don't have any trend in the frequencies, so we'll just sample each frequency independently. And so it gives a sort of a more conservative, I guess, uncertainty estimate.
Okay, thank you.
Thank you.
Any further questions? Thank you, Samuel, once again. And thank you to all the speakers for keeping to time. That's given us now an opportunity to have a few moments now to have some general questions and an open discussion on this whole aspect of metrology inputs into field calibration of IMS measurement systems. I think, do we have that summary slide to show? Well, before we get into that, are there any immediate questions for any of the presenters that couldn't be asked at the time? Are we all up to date with questions? Was there anything online that we need to?
No.
Okay, so nothing coming from online. So what we've seen in the talks today is that there are kind of different stages in the thinking process in order to reach a field calibration and get data from that field calibration, as Samuel nicely showed in his presentation. And those steps start in the laboratory with the primary calibrations. We've had some talks on methods of primary calibration of the different types of sensors we use for the waveform technologies in the IMS. And the next stage is how we get that capability from the laboratory into the field. So kind of a transfer calibration process, and the Schmidt system that, again, Samuel showed is an example of that, and there are other examples for different technologies. And then the third step is how to then implement the field calibrations in an ongoing basis as part of the routine monitoring activity that the IMS undertakes. So I think yesterday we had a quick look at the kind of state of play in each of those steps, the lab calibration, the lab to field calibration, and the field calibration itself in each of the three technologies. So we had a bit of a brainstorm to try and put a pin in where we are in each of those steps in each of the technologies.
And Chan showed them as part of his talk, where he was explaining the current status of each of them. And this is a summary slide showing the status of each of them essentially in one slide as a suggestion of what to talk about. The red is where we're not yet sure of what all the solutions are. The orange is maybe solutions have been proposed but not yet implemented. For yellow, they're being evaluated, and for green, the solutions are implemented, and you can see there's not a lot of green in this plot. So I think what we are looking for is suggestions for any of the particular topics, or for broadly across them, how we can get closer to green.
Yeah, so really it's over to the audience to kind of express some views on this, if they've got any suggestions for how we progress each of the areas, any comments or concerns about the approaches being taken. I think these are all sort of useful topics to hear about.
Just have a question, sir. I didn't see your earlier presentation. So I understand lab, I understand field. What does lab to field mean exactly?
So my understanding is how you get the laboratory-based capability into the field. I think in John's presentation he mentioned that there are some very nice laboratory calibration capabilities. They're beginning to understand what impacts the uncertainty and the actual possibility to implement these in the lab. So that's developing quite well. But as John said, that's in the lab and you need it in the field. So you need the calibration capability in the field. So how do you make that transfer from one place to the other? What type of sensors do you use? What kind of methods do you use to take that laboratory capability and put it in the field? That's kind of what we mean there. It's the transfer process.
So for example, for the hydroacoustic, the laboratory calibrations are all done under very controlled conditions, whereas you then have to transfer that calibration to a device which will be used in the field and will be used in the conditions that exist in the ocean, which might be quite different from laboratory conditions. So you have to be able to calibrate it at conditions that are representative of those in the ocean as well. For example, the correct depth or temperature, which may not be applicable in the very precise calibrations you do in the laboratory. So it's really transferring your highly accurate laboratory calibrations to applicable calibrations for that exist for the field conditions. And then the field is really the sort of in situ calibrations. How do you go about doing a calibration actually in situ? So I think that's the three processes we envisaged. Yes, Richard? Peggy?
I think so. I mean, this was really put together with a small discussion with some of us before we met today. It'd be interesting to know if you've got other perspectives, other kind of thought processes into how all of these things develop and how we get to that point of field calibration.
The speakers have a microphone to share, and the other people will.
I would like to turn this whole thing around. Sorry, I'm going to be provocative, but you asked what is the difference between lab and field, right? That was your question. What does it mean? When you think about an example from seismology, and now I'm naming names, although I had in my disclaimer that I was not going to name names, but the STS-1 was one of the first broadband instruments that was deployed at all. And we only noticed after 20 years of operation in the field that something was deteriorating in the sensor. You would have never found this, Thomas, I'm sorry, you would have never found it in your lab because, you know, I don't know how long you've worked at PTB, but certainly 20 years of operations, that showed that this instrument was slowly deteriorating. So that's why I try to explain in my talk that we should have a more comprehensive look, the state of health of the whole system. That is the important part. It's not necessarily one element. it is the state of health of the whole system. So we should, when we talk about field, we should really think about how all the knowledge that we have accumulated about seismic instrument or infrasound instruments or hydrophones, how that evolves over time through the field measurements. And that you can only do that when you really take all the different elements into account. So I don't think that there is a difference between laboratory and field, because the field sometimes, at least for seismology, is the laboratory, because we can't replicate all of the things that nature presents to us in the field. I don't know. I'll hold it.
Well, Erling Sanderman from HBK in Denmark. I have a comment. I agree very much in what you're saying, but I don't see the contradiction. Because we still have to make the primary calibrations and carry them out. And that is more or less the question from that slide. I agree completely that you have to look at all the other things in the field to make sure that you make solid measurements in the end. But I also have a comment to the figure that you have set up there. I like it a lot. But I also think that we have demonstrated, and we have demonstrated to the talks at this conference and also 2 years ago, that there's a big momentum. You can also see there's more people coming to this. So there's a more momentum in being realistic on traceability, taking into that into account, but also a lot of work is being done for the time being. Things are coming up slowly. So I think that figure is becoming more and more green, but at the same time, it's very important that we pinpoint the places where we miss information, where we need more research.
So I would like to follow up with that, and I think that yes, I'm going to call that adoption, and I think that it's clear there's a group of people who think it's important, but from the seismic point of view, there are probably hundreds of operators of seismic stations and networks who really don't know anything about this and think that they're happy the way they're going on. And so part of the lab to field is the technical part where we develop and test the means of getting it into the field, but part of this lab to field part is also the part where we proselytize the value and explain to them what they're getting from this improvement, what we're calling an improvement of their operational tasks.
Yeah, I completely agree. We've been talking mostly about technological developments today and how we get from red to orange to green on this chart, for example, but there's a whole complementary piece about disseminating the information, training, engaging with the community to propagate these advantages and get them to understand the advantages and the benefits to their work, and then to adopt the procedures, I guess is another job altogether.
I think we may have a question or comment online. Can we go there?
Hi, I had a question about the yellow rating for the hydroacoustic lab calibration. Is that yellow, will that yellow turn green after we do international comparison for frequencies in the 1 hertz to 100 hertz range?
Yes, it will go, well, more greener. Yes, it will. Yes, it will go. That's for the primary calibrations, that's the bit that's missing at the moment. Yes, it will. It will go greener, yes.
Okay, thanks. And then a second comment on monitoring the overall health versus just calibration. My impression is that the hydroacoustic stations, the electrical calibration is only the digital side of the system. Is that true?
No, it's there's an analog signal injected. It's like an insert voltage calibration. So the electrical analog signal is injected between the hydrophone element and the preamplifier, and then checks the entire measurement chain. So it's not just a digital signal.
As far as I know, just the electrical part.
Yeah. But it's not. It's an injection of an electrical signal. It's not a digital.
Electrical, but just to the electronics.
Yeah. So it's a lot of hydrophones, even commercial ones, have an extra wire which allows you to inject a signal between the element and the amplification. So it's the same principle.
Okay, thanks. And last question is, has there been any discussion of using unmanned underwater vehicles for getting hydrophones near the IMS stations for calibration? I wonder if that's cheaper or easier than sending a ship out and then trying to dangle the equipment off a ship.
Yeah, I remember that being raised by a former member of staff at CTPTO, Peter Nielsen, once a few years ago, but it hasn't really been explored. So if that can be done, if there are ways of doing that, I'm sure they'd be interested. But that was only talk. No one's tried it.
Okay, thank you. That's all my questions.
Jan, do you want to say something in response?
Yeah, in general, I would like to say, first of all, thanks. From the supplier, from the neither side, I just want to highlight that this sustainment of the IMS network is a very hot topic, and the PTS is working on that so hardly. I can say for hydroacoustics, the stations, actually the underwater systems run until they fail, so there should be a potential application area for us to go and check the full chain characteristic of the hydrophone stations to see if there is any degradation on the full chain. So based on this evaluation, we would like to make our plans to sustain the network for the hydroacoustic component, because these stations has to run 7/24, and the data availability should be over 98% through the years. So if there is any kind of failure on the system, it can be on the hydrophone side or on the analog part side. The recapitalization of the station is not so easy. So you have to plan a project that can take a year or a couple of years. So that's why during this failure period, the station goes off. And as you consider there's only 6 hydrophone stations, the data availability drops below the mandate. So therefore, there is a huge request from our side to implement that in-situ calibration to see if, because these stations are deployed 25 years ago, so they are not new, and we cannot evaluate the analog part of the station, just the electronic part is evaluated and compared with the initial calibration. So that's the reason that we would like to somehow implement it. It can be as it was discussed, with some techniques that are on the standards, or there can be now some new proposals from the meteorology community to run those calibrations. So we are really looking forward to make this collaboration with the institutions who have these capabilities and try to figure out to check the full chain. Yeah, thank you.
Okay. Any further questions? Anyone like to say something? Yes, a couple of people towards the back.
If you don't mind, I'd like to come back to the lab-to-field calibration. I really appreciated Jeff's clarifying question because it wasn't clear to me either. But now I get it. This is very much about accounting especially for temperature differences, with hydrophones also pressure differences, so we need models for these things. And we saw I was just double checking the slides, Stephen Robinson's slides showed, where are you? Anyway, showed the sensor response across frequency at various temperatures. And the characteristic was very strange. It wasn't obvious to me what the pattern was with temperature. And I want to contrast that with what I've seen in my work, and I think I see it in some of John Merchant's work too, with seismometers, where the change in response to temperature is very much associated with specific components and specific poles and zeros in the sensor response. And I feel like if we're going to transfer the behavior of the instrument to the field, we need models for how the instrument response is going to change as a function of temperature or pressure. And those models likely need to be expressed in terms of poles and zeros, and then even more fundamentally, sometimes identifying which component in the system is dominating that pole or that zero. So if you're talking about a seismometer, a passive seismometer, the resonant frequency is set by the mainspring stiffness and the mass. And the mass isn't going to change with temperature, but the mainspring stiffness is. And similarly for almost every other component, I think having these kinds of models is going to be really helpful if we're going to expect to be able to deploy the instrument under different conditions and expect to be able to predict what that response is. So that means we need to, I think, get away from the frequency amplitude phase representation a bit and use poles and zeros more so that we can model them, see how they change with temperature. And also, I think it needs to be coming from the manufacturer what the expected temperature sensitivity is, and then verified by the lab, and some back and forth and feedback there.
Sorry, can you call it sensitivity to temperature? Because the temperature sensitivity has another connotation in other things that we're talking about.
Very much. I hear myself saying these slightly confusing things, but yes. Yes, not only is the sensitivity, the mid-band sensitivity, let's say, going to be sensitive to temperature, but the high frequency and low frequency roll-off is controlled by parameters, and they will have temperature sensitivities too. I hope is that clear?
Yeah, thank you.
So I've been trying to use the term susceptibility. If that's...
There you go. Yes, maybe that's what I should do. Thanks.
Get it from him.
So there's a gentleman at the back on the aisle as well that's been waiting to ask a question.
I just wanted to give a very short comment on the same topic, Richard.
Yeah, do.
I would like to ask, from the laboratory side, I would like to ask for some patience, because we need to have reliable methods as a ground truth, and then we can start to change temperatures and apply the same methods. So we need some more time.
Thank you. Please.
Thank you. I think at the end of the session, there's a high time to remind something specific about the CTBTO observation related to the seismic network. What I wanted to say that we shouldn't forget that it seems to me the CTBTO, the only network which is running simultaneously about 40 arrays, and many of them are running in the boreholes. So boreholes means that we have a special mechanism to install the hole lock mechanisms and to take care about the clamping of the instruments to the ground. We call it coupling or whatever. So this is an important component which is making an impact on the high frequency domain shape of the response. And there are a lot of presentations about the difficulties to feed with the nominals for the high frequency observations. And so there is, it seems to me, no way to reproduce either using the reference sensor method or the electrical calibration, because it's not a true ground motion, to make definition of the quality of the clamping of the instruments to the borehole, because of the difficulties to reproduce the same conditions for the clamping, even we are using reference sensor or whatever. So this is an important component to add to the consideration of the improvement of the calibration and traceability components of the network, because high-frequency components of the signals is very important for the verification and the screening criteria to distinguish between natural events and the explosions. Thank you.
Yeah, I think that very valid point, actually, and I think that's something that is understood is we need to also think about the mounting configuration and how that is influencing
broadly the environment.
Yeah, the installation environment.
Yes, so I was thinking, yesterday there was a presentation that mentioned it, Horst mentioned it at the end of his talk, I think. There were several others. I mean, for a seismic system, if we put 2 instruments in that have had the secondary calibration as part of their initial process development, processing, construction, whatever, and then we install them in the same place, then their environment is going to be the same. More or less, their temperature is going to be the same. And if over the course of their installation, they suddenly diverge from each other, what they're recording, then that would be an indication at least that something is wrong. Because normally things don't go wrong the same way in 2 instruments at the same time, unless it's a lightning strike and nothing comes out of them anymore. But that's clear that then that's a definite problem. I know that at Berkeley, one of the things we do, because we really hate to stop the recording and interrupt it, is that rather than doing regular calibrations of the stations, we have simply compared the data from the accelerometer and the broadband instrument, and if it stays the same, they agree, then we're happy, and if it doesn't stay the same, then we start troubleshooting. So that's one way of doing it, and if your accelerometer and your broadband instrument, or your accelerometer and your S13 have both been pre-calibrated before they go into the field, and then they're sitting there and working in the same way, quote unquote, all the time, then it's good. The state of health is good, and if something changes, then the state of health is not good, and one can go back and figure out how to either do the recalibration or to change one of the instruments. Idea.
So Peggy, I was just going to say that that's a great example of an operational in situ comparison, similar to what we're showing, and
yes.
Probably a good starting point. It's what's done in some of these regional earthquake warning networks and GSM networks that have those accelerometers that perhaps, you know, our stations could learn from and leverage to move that orange to yellow.
Make the seismology greener.
Yeah, or yellow at least.
Richard, I have a very small comment. Now you talked about that yesterday with the same temperature in the field, but if the 2 sensors are different, they may not have the same dependence on temperature, so they may diverge if the temperature in the vault changes, even though they are still working properly.
Well, if temperature performance is a required part of the calibration process, then, and we use the full instrument response, then presumably one could follow that. I can say that when I was a young seismologist, it was really important to have the temperature at the station be as constant as possible. And now that I'm an older seismologist and there are many, many more stations, there are many fewer, well, the percentage of stations where such high quality temperature demands are made of the station is much lower.
Yeah, I agree with you, Peggy, and I think also we can look at it, at least from the infrasound, where we have already implemented the calibration at several stations. We even find it to be a more robust method to use different instruments when we use collocated sensors, exactly to detect this kind of problem, and we have, yes.
But I want to say, following up, in the long run, deploying 2 instruments at the same time is a small relatively small instrument cost, but having people go out once or twice a year to deploy something and interrupt the measurements is a much bigger cost, because in some countries at least, people are more expensive than instruments. It's like why the reason we replaced horses with cars is because for the car you only had to fill it up with gasoline occasionally, and for the horse you had to feed it every day.
And I was just going to say that I think one aspect of this in situ approach for these long-term installed, whether either seismometers or infrasound sensors, is what's the process and periodicity for having that in situ reference rechecked, and that's something on the to-do list.
Okay, I'm conscious of the time. I know we need to vacate this room within a few minutes. So probably just to wrap up very quickly, I think this graphic has a lot of value actually for the simplicity of it. There's a lot you can infer from it. So I think this will be a very useful marker going forward. I just wanted to say that if you're interested in this topic and you have further comments, if you remember the very first slide that Jan produced, showed, has some contact details. So please do get in touch with any further remarks or comments, because all of this will help future development and deployment of these types of issues. So thank you. If you've been here for the whole session, thank you very much for sticking with it. Thank you all for participating, and thank you again to all the presenters and my co-chairs, of course.
Yes, maybe just a small addition. There are posters tomorrow in poster session 3.1, which are very relevant to this topic. So, yeah, if you're interested.
And that's tomorrow afternoon, is that correct?
No, 12. 11 for the lightning and 12 for the poster
Yeah, but
session.
it's posters. So not all of the posters are at 12. You go there at 12 and look at all of the posters.
Yes.
Okay, thank you.